Hey everyone, tonight we're diving into something that's going to change how you think about what it means to be human. We're talking about climate change, but not the kind dominating headlines today. This is the story of how our planet's shifting moods over millions of years literally sculpted us into the species we are now. Every breath you take, every step you walk upright, even the way your brain processes these very words, it all traces back to ancient skies that reigned differently, temperatures that swung wildly, and landscapes that transformed faster than any Hollywood special effect. So grab something comfortable to drink, maybe dim those lights a bit, and let's journey back to a time when being human meant something completely different. Because what we're about to explore isn't just history. It's the most intimate biography ever written, carved not in stone, but in our very DNA. Picture this. You're standing in the East African Rift Valley about 2.5 million years ago. The air tastes different here, thick with volcanic ash and the promise of rain that may or may not come. Around you, the landscape shifts like a living thing. Where lush forests stood last century, now grasslands stretch toward distant mountains. Where reliable water sources once bubbled, now dry creek beds snake through cracked earth like ancient scars. This isn't just scenery changing. This is evolution's laboratory in full swing, and our ancestors are the test subjects. Every environmental curveball thrown at them becomes a choice point. Adapt or disappear. Change or become fossil fuel for future paleontologists to puzzle over. And here's the thing that's going to blow your mind. The climate didn't just influence human evolution. According to the latest research emerging from institutions like the Smithsonian and major universities worldwide, climate variability was the primary driving force behind nearly every major leap forward in human development. We're talking about a relationship so fundamental that without these ancient climate swings, you probably wouldn't exist as the thinking, planning, tool-making creature you are today. Now, before we go any further, let me tell you why this story matters beyond just satisfying curiosity. Understanding how climate shaped our evolution isn't some dusty academic exercise. It's the key to understanding human adaptability, resilience, and survival instincts that are still hardwired into your brain right now. It explains why humans became the most geographically widespread species on Earth. Why we're the only animals that actively modify our environment instead of just adapting to it. And why, when faced with challenges, our first instinct is to innovate rather than just endure. The traditional story you might have learned in school painted human evolution as a steady march from ape to human, driven by gradual changes in habitat. Forest disappeared, savanna appeared, and our ancestors started walking upright to see over tall grass. Simple, clean, wrong. The real story is far more dramatic. It's a tale of rapid climate oscillations that would make modern weather forecasters weep with confusion. Periods where the climate of East Africa would swing from lush, lake-filled paradise to arid desert and back again within spans of just 20,000 years. That might sound like a long time to you, but in evolutionary terms, it's the blink of an eye. These weren't gentle transitions. We're talking about environmental whiplash on a continental scale. Imagine if your hometown went from tropical rainforest to desert to frozen tundra every few thousand years, and you had to not just survive each transition, but thrive in it. That's exactly what our ancestors faced, and it forged them into something unprecedented in the history of life on Earth. The evidence for this climate-driven evolution story comes from one of the most remarkable scientific achievements of the past few decades. Deep in Kenya, at a site called Olorgesailie, researchers have drilled cores from ancient lakebeds that preserve a detailed record of environmental conditions stretching back 700,000 years. These cores are like nature's own hard drives, storing information about rainfall, temperature, vegetation, and atmospheric composition with precision that would make modern meteorologists jealous. What these cores reveal is staggering. For hundreds of thousands of years, the environment remained relatively stable. Our early ancestors developed a successful lifestyle based on large stone tools and predictable resources. They had figured out their world and were doing just fine, thank you very much. Then, around 400,000 years ago, everything changed. The geological evidence shows that massive tectonic activity began reshaping the region. The landscape itself became segmented, with new hills and cliffs rising, huge lakes draining away, and the entire ecosystem becoming hypersensitive to climate variations. What had been a stable environment became a chaotic patchwork of rapidly shifting conditions. And here's where it gets really interesting. Instead of driving our ancestors to extinction, this environmental chaos sparked them to make major leaps forward in behavior and culture. They developed more sophisticated stone tools and weapons. They expanded trade networks across hundreds of kilometers. They even began showing evidence of symbolic communication, the foundation of human language and culture. This transformation wasn't gradual. The archaeological record shows rapid, almost explosive changes in human behavior, coinciding exactly with these periods of maximum environmental instability. It's as if crisis became the catalyst for everything that makes us uniquely human. But let's zoom out and look at the bigger picture, because the story of climate and human evolution goes far deeper than just one site in Kenya. Across Africa and eventually across the globe, our ancestors were writing the playbook for environmental adaptability that no other species has ever matched. The secret lies in something scientists call variability selection. This concept, developed by Dr. Rick Potts at the Smithsonian Institution, revolutionizes how we think about evolutionary pressure. Traditional thinking suggested that species evolved to become perfectly adapted to specific environments. Giraffes develop long necks for reaching high leaves. Polar bears develop thick fur for Arctic conditions. Each species finds its niche and optimizes for it. But humans took a completely different path. Instead of becoming specialists perfectly adapted to one environment, we became the ultimate generalists, capable of thriving in virtually any environment Earth could throw at us. And the driving force behind this unprecedented adaptability was environmental variability itself. Think about it this way. If you live in a stable environment, it pays to specialize. Develop the perfect tool for the perfect job, and you'll outcompete everyone else using that tool. But if your environment keeps changing, specialization becomes a death trap. What you need instead is flexibility, creativity, and the ability to rapidly develop new solutions to novel problems. This is exactly what happened to our ancestors. The climate of East Africa became so variable, swinging between extremes so rapidly and unpredictably, that the only survival strategy was to become really, really good at adapting to change itself. And that's how humans became the Swiss Army knife of the animal kingdom. The evidence for variability selection is written in our bones, our brains, and our behavior. Take brain size, for example. The most dramatic increases in human brain volume occurred during the periods of greatest climate instability, not during stable periods when bigger brains would have been metabolically expensive luxuries, but during the chaos when larger brains capable of processing complex, changing information became survival necessities. These larger brains allowed our ancestors to do something no other species had ever done on such a scale. They could process and store information about multiple different environments, plan ahead for various possible futures, and solve abstract problems that had never been encountered before. A large brain capable of producing versatile solutions to new and diverse survival challenges became the ultimate adaptation to an unpredictable world. But brain evolution was just one piece of the puzzle. The archaeological record shows that technological innovation also accelerated during periods of climate instability. After 400,000 years ago, when environmental conditions became most variable, hominins found completely new ways of coping with their world by creating diverse toolkits. Where once large, standardized cutting tools dominated, Smaller, more specialized implements appeared. Projectile points for hunting at a distance. Hafted tools that combined multiple materials for specific tasks. Sophisticated processing implements for extracting nutrition from previously inedible resources. Each new tool represented a solution to environmental challenges that previous generations had never faced. Tool use didn't just help our ancestors obtain food more efficiently, it fundamentally widened their dietary options and, by extension, their ability to survive in different environments. Meat, in particular, became obtainable in equivalent ways, with similar nutritional value in virtually any habitat early humans encountered. Whether in grasslands, woodlands, or transitional environments, the ability to hunt and process animal protein provided a buffer against plant resource variability. The development of stone tool technology also reveals something fascinating about early human cognition. Making sophisticated stone tools requires planning ahead, understanding material properties, and maintaining mental templates for desired end products. These are all higher-order cognitive functions that distinguish human thinking from that of other animals. More importantly, the carrying of stone tools over considerable distances and becoming reliant on stone technology may have arisen specifically due to the benefits of dietary flexibility as environments changed. Our ancestors were literally carrying their adaptability with them, in the form of portable technology that could be applied to whatever challenges they encountered. But perhaps the most remarkable aspect of climate-driven human evolution was the development of social cooperation and trade networks. By 130,000 years ago, hominins were exchanging materials over distances of more than 300 kilometers. This isn't just impressive logistics for people without pack animals or wheeled vehicles. It represents a completely new survival strategy based on social relationships and mutual aid. Trading between groups to obtain materials and cement alliances became a hallmark of modern human behavior. The social bonds forged by exchanging materials between groups may have been critical for survival during times of environmental change, when one group needed to rely on the resources or territories of distant groups. Think about the implications of this. Instead of each group having to independently solve every environmental challenge, human societies began developing networks of shared knowledge and mutual support. If one region experienced drought while another had abundant water, established trade relationships could mean the difference between survival and extinction. This social innovation was just as revolutionary as any technological advancement. It meant that human adaptability was no longer limited to what individuals or even single groups could accomplish. It became a species-wide phenomenon, with innovations and solutions spreading rapidly across vast distances through social networks. The development of symbolic communication during this same period wasn't coincidental. Complex language abilities allowed human groups to share detailed information about environmental conditions, resource availability, and successful survival strategies across both space and time. Knowledge gained by one generation in one location could be preserved and transmitted to future generations facing similar challenges elsewhere. Archaeological evidence for symbolic artifacts, complex language, and long-term planning appears in the record precisely during periods of maximum environmental instability. These weren't luxury developments that appeared during easy times. They were survival tools forged in the crucible of climate chaos. But the story gets even more interesting when we look at how these climate-driven adaptations enabled the first major expansion of human populations beyond Africa. The migration of Homo erectus around 2 million years ago represents the first major test of human adaptability to completely new climates and environments. Recent research shows that when Homo erectus migrated from Africa, climate conditions created what scientists call a green corridor through northeastern Africa and the Middle East. Areas that are mainly desert today were then wetter and more vegetated, providing a pathway for human expansion into Eurasia. This migration wasn't just a one-time event. It demonstrates how climate windows of opportunity enabled human expansion into new territories. and how our ancestors had developed the behavioral and technological flexibility to take advantage of these opportunities when they arose. The success of this expansion is remarkable. Fossil evidence for Homo erectus stretches over more than 1.5 million years, making it by far the longest surviving of all our human relatives. Compare this to our own species, Homo sapiens, which has existed for perhaps 400,000 years, and we begin to appreciate their extraordinary ability to survive through many changes in environment and climate. Even more impressive, once Homo erectus reached Southeast Asia, they migrated across the region at remarkably fast rates, covering more than 10 kilometers per year. This rapid migration rate suggests that early humans had developed sophisticated behavioral and technological adaptations that enabled them not just to survive in diverse environments, but to actively seek out and colonize new territories as climate conditions became favorable. The implications of this early human expansion are profound. It means that by 2 million years ago, our ancestors had already developed the core adaptations that would eventually allow our species to colonize every continent except Antarctica. The foundation for human global dominance was laid not during recorded history, but during the Pleistocene epoch, in response to the climate variability that characterized that period. As we continue this journey through deep time, we'll explore how these early adaptations to climate variability set the stage for even more dramatic evolutionary developments. We'll see how the relationship between environmental challenges and human innovation continue to drive our species toward the remarkable cognitive and cultural abilities that define us today. Us today. The story of how our ancestors navigated these climate challenges becomes even more fascinating when we examine the specific physiological changes that emerged during periods of environmental instability. Around 1.8 million years ago, something extraordinary happened in the fossil record. Multiple new hominin species appeared almost simultaneously, and among them was early Homo erectus, with a brain 80% larger than its predecessors. This wasn't gradual change. This was rapid evolutionary response to new ecological conditions, particularly the appearance of deep freshwater lakes in the East African Rift Valley. The timing is too precise to be coincidental. Statistical modeling comparing lake and climate records with evidence of human evolution provides the strongest evidence to date for what scientists call the pulse climate variability hypothesis. Originally proposed in 2009, this theory states that at 2.6, 1.8, and 1 million years ago, there were short periods of around 200,000 years when East Africa became extremely sensitive to changes in Earth's orbital patterns. The result was rapid cycling between very dry and very wet periods of about 20,000 years each. Picture the drama of these transitions. Due to orbital changes, the climate of East Africa oscillated between having huge, deep freshwater lakes surrounded by rich, lush vegetation and extremely arid conditions with sand dunes covering the floor of the Rift Valley. These weren't gentle seasonal changes. These were complete ecosystem transformations, happening faster than any single generation could adapt to through traditional evolutionary mechanisms. But here's where human evolution took its most decisive turn. Instead of being victims of this environmental chaos, our ancestors became masters of it. The bigger brains that appeared during this period weren't just larger storage containers for information. They were fundamentally different kinds of processing units, capable of handling the complex, abstract thinking required to survive in rapidly changing environments. These enhanced cognitive abilities manifested in ways that still define human behavior today. Planning ahead became not just useful, but essential. Understanding cause and effect relationships across longer timescales meant the difference between thriving and disappearing. The ability to create mental models of different possible futures and prepare for multiple scenarios simultaneously became a core survival skill. The archaeological evidence for this cognitive revolution is written in stone, literally. The tool technologies that emerged during periods of maximum climate variability show unprecedented sophistication and standardization. But more importantly, they show something that had never appeared in the fossil record before: evidence of teaching and learning across generations. Creating the advanced stone tools found at sites from this period requires not just individual skill, but cultural transmission of knowledge. The techniques involved are too complex to be figured out independently by each person. They had to be learned through observation, practice, and instruction. This means that by 1.8 million years ago, human societies had developed formal methods for preserving and transmitting crucial survival knowledge. The implications extend far beyond toolmaking. If our ancestors were systematically teaching each other how to create sophisticated implements, they were also sharing knowledge about environmental patterns, resource locations, seasonal timing, and survival strategies. Climate variability had forced the evolution of culture itself as a survival mechanism. But the relationship between climate and human development becomes even more intricate when we examine the role of fire in early human evolution. Around 2.5 million years ago, something transformative happened to human diet and behavior that scientists believe was directly linked to environmental changes in East Africa's Great Rift Valley. The volcanic activity that characterized this region during periods of climate instability may have provided early access to naturally occurring fires. Learning to control and maintain fire represented a technological breakthrough that fundamentally altered human evolutionary trajectory. But the timing suggests this wasn't just opportunistic innovation, it was adaptive response to environmental pressure. Cooking food through controlled fire use explained the dramatic changes observed in early human anatomy during this period. Mouths, teeth, and digestive tracts began evolving in ways that reflected a completely new dietary strategy. Most importantly, this new diet allowed brains to grow exponentially in size, leading to massive changes in behavior and intelligence. The caloric link between cooked food and brain evolution cannot be overstated. Larger brains are metabolically expensive, requiring enormous amounts of energy to develop and maintain. Raw food diets simply couldn't provide sufficient calories to support the kind of brain growth observed in the fossil record. But cooked food unlocks nutrients and makes them more easily digestible, providing the energy surplus necessary for dramatic neurological development. Fire mastery also provided additional survival advantages that proved crucial during periods of climate instability. Warmth during cold periods meant humans could survive in environments and seasons that would have been lethal to earlier hominins. Protection from predators through controlled fire use allowed expansion into territories that had previously been too dangerous to occupy. Perhaps most importantly, fire provided a social focal point that encouraged group cohesion and communication. Gathering around fires for warmth, cooking, and protection created opportunities for information sharing, planning, and cultural transmission that wouldn't have existed otherwise. The hearth became humanity's first classroom, laboratory, and social center, all in one. The mastery of fire also demonstrates something crucial about human adaptability that distinguishes our species from all others. Instead of simply adapting to environmental conditions, humans began actively modifying their immediate environment to suit their needs. This represents a fundamental shift in the relationship between organism and habitat that has defined human ecology ever since. As climate continued to drive human evolution, the development of increasingly sophisticated social structures became both cause and effect of our species' success. The trade networks that began appearing by 130,000 years ago weren't just economic systems. They were information networks that allowed rapid sharing of innovations and survival strategies across vast distances. Consider what this meant in practical terms. A group facing drought in one region could access not just material resources from trading partners, but knowledge about water sources, alternative food supplies, and survival techniques developed by groups in different environments. Climate variability had forced the evolution of collective intelligence that transcended individual group limitations. The archaeological evidence for these early trade networks reveals something remarkable about human cognitive development. Materials found at archaeological sites often originated hundreds of kilometers away from where they were used. This indicates not just the ability to transport objects over long distances, but sophisticated understanding of value, exchange relationships, and delayed gratification. Trading valuable materials with distant groups requires abstract thinking about future needs, trust in reciprocal relationships, and complex social negotiations. These cognitive abilities developed specifically in response to environmental challenges that required cooperation between groups for survival during climate-driven resource shortages. But the story of climate-driven human evolution takes another dramatic turn when we examine what happened in different regions of the world as early humans began expanding beyond Africa. The Neanderthals of Eurasia provide perhaps the most compelling example of how sustained environmental pressure could drive specific evolutionary adaptations. Neanderthals inhabited glacial climates for over 100,000 years, repeatedly enduring conditions that ranged from seasonally cold to full glacial periods. Unlike their African relatives who dealt with variable but generally warm climates, Neanderthals faced the consistent challenge of extreme cold that required completely different adaptive strategies. Their morphological adaptations to cold environments were remarkable and highly specialized. Broad trunks and shortened limbs provided relatively high body volume with lower surface area, maximizing potential metabolic heat production while minimizing heat loss. Robust muscular development and dense bone structure supported the high-energy lifestyle required for cold weather survival. These physical adaptations were supported by equally specialized behavioral strategies. Neanderthals developed sophisticated hunting techniques focused on large-bodied game animals that provided the enormous caloric intake their high metabolism bodies required. Deer, ibex, wild boar, aurochs, and occasionally mammoth and woolly rhinoceros became frequent components of their diet. The Neanderthal example demonstrates how environmental specialization could be both an advantage and a vulnerability. Their adaptations to glacial conditions made them extraordinarily successful in Ice Age environments, allowing them to thrive in territories that would have been impossible for other hominins to occupy. However, their specialization also made them vulnerable when climate conditions changed rapidly. Research suggests that because Neanderthals relied heavily on protein from large game animals, they struggled to adapt when climate changes impacted populations of those animals. Environmental shifts that transformed open woodlands into Arctic-like steppes disrupted the ecological relationships that had sustained Neanderthal populations for millennia. The contrast between Neanderthal specialization and early modern human generalization illustrates a crucial principle of climate-driven evolution. Moderate environmental variability tends to favor adaptability and flexibility, while extreme or consistent environmental pressure favors specialization. The climate history of Africa, with its rapid oscillations between different conditions, selected for generalist strategies that proved more successful in the long term. This principle becomes even more apparent when we examine the technological innovations that emerged during the Middle Stone Age in Africa. Between 280,000 and 30,000 years ago, anatomically modern humans developed increasingly sophisticated tool technologies that reflected their growing mastery of environmental challenges. Archaeological evidence from this period shows technological innovation occurring in distinct pulses that correspond precisely with periods of rapid climate change. Major innovational advances happened when South African climate changed rapidly toward more humid conditions, while northern sub-Saharan Africa experienced widespread droughts as the Northern Hemisphere entered phases of extreme cooling. The correlation between technological innovation and climate change during this period is so precise that researchers have identified what they call a striking correspondence between the archaeological record and the timing of abrupt climate shifts. All major technological advances fell within periods of rapid environmental transition suggesting that crisis continued to be the primary catalyst for human innovation. These Middle Stone Age innovations weren't just improvements in existing technologies. They represented fundamentally new approaches to resource extraction, food processing, and environmental management. Smaller, more diverse toolkits replaced the large cutting implements that had dominated earlier periods. Projectile technologies allowed hunting at greater distances, and with improved success rates. Hafted tools combined multiple materials to create implements specifically designed for particular tasks. Perhaps most significantly, symbolic artifacts indicating complex language abilities and long-term planning began appearing in the archaeological record during this same period. Ochre pigments used for body decoration, engraved objects with geometric patterns, and shell beads transported over long distances all point to the emergence of symbolic communication and abstract thinking abilities. The development of symbolic communication represents another crucial adaptation to environmental uncertainty. Complex language allows human groups to coordinate responses to changing conditions, share detailed information about resource availability across both space and time, and preserve crucial survival knowledge for future generations. But symbolic communication also enabled something that no other species had ever achieved: the ability to share abstract concepts and mental models across individuals and generations. This meant that human adaptability was no longer limited by individual experience or even group memory. Knowledge and innovations could be preserved, modified, and transmitted across vast networks of human societies. The emergence of these advanced cognitive and cultural abilities during periods of maximum climate stress demonstrates how environmental challenges continue to drive human evolution, even after the basic template of modern human anatomy had been established. Physical evolution was increasingly supplemented by cultural evolution as the primary mechanism for adapting to environmental change. This shift from primarily biological to primarily cultural adaptation represents one of the most significant transitions in evolutionary history. Instead of waiting for genetic changes to provide better environmental fit, humans began developing cultural solutions that could be implemented within single generations and shared rapidly across populations. The speed of cultural adaptation compared to biological evolution meant that humans could respond to environmental challenges faster than any other species. New tools, techniques, and social strategies could be developed, tested, and refined within years or decades, rather than the thousands of generations required for significant genetic change. But cultural evolution also introduced new complexities into the relationship between climate and human development. Different human populations began developing distinct cultural adaptations to their specific environmental challenges, leading to the extraordinary diversity of human societies that characterizes our species today. Regional climate differences during the Middle to Late Pleistocene led to technological diversification between different areas. Human populations in northwestern Africa, associated with colder, drier, and less productive environments, developed different technological strategies than those in eastern Africa's more variable but generally warmer conditions. Northwestern African Middle Stone Age populations invested heavily in specific risk mitigation strategies for dealing with seasonally mobile resources and more predictable but harsher climates. Eastern African populations developed more diversified toolkits, reflecting the need to adapt to rapidly changing tropical environments with high resource variability. These regional differences in technological adaptation demonstrate how climate continued to shape human cultural evolution, even after our species had developed the basic cognitive abilities that characterize modern humans. Environmental challenges remained the primary driver of innovation, but the responses became increasingly sophisticated and culturally mediated. The relationship between climate and human cultural diversification also reveals something important about the nature of human adaptability itself. Instead of developing a single optimal strategy for dealing with environmental challenges, different human populations experimented with multiple approaches, creating a reservoir of cultural knowledge that could be drawn upon as conditions changed. This diversification of adaptive strategies represents a form of collective insurance against environmental uncertainty. If climate changes made one approach ineffective, alternative strategies developed by other populations could be adopted and modified to meet new challenges. Cultural diversity became a species-level adaptation to environmental unpredictability. The success of this approach is evident in the unprecedented speed of human expansion across diverse environments during the late Pleistocene. By 40,000 years ago, modern humans had successfully colonized environments ranging from tropical rainforests to Arctic tundra, desert oases to high-altitude plateaus, coastal marshlands to continental grasslands. Each of these environments presented unique challenges that required specific adaptive strategies, yet humans were able to develop successful solutions within relatively short periods. This environmental versatility was unprecedented in the history of life and reflected the cumulative effects of millions of years of climate-driven evolution. The computational models now being used to test hypotheses about climate-driven human evolution reveal patterns that weren't visible through traditional archaeological methods. These models can simulate the effects of different climate scenarios on human population dynamics, technological innovation rates, and migration patterns with remarkable precision. Results from these computational studies consistently support the variability selection hypothesis, showing that periods of moderate environmental instability produce the most rapid advances in human cognitive and cultural evolution. Stable environments led to technological stagnation, while extreme instability led to population crashes. But moderate variability drove continuous innovation and adaptation. The models also reveal how seemingly minor climate changes could have cascading effects on human evolution through their impacts on resource availability, predator populations, disease transmission, and social interaction patterns. Environmental changes that might seem insignificant from a modern perspective could trigger major evolutionary responses when they affected critical survival resources. Perhaps most importantly, these computational studies demonstrate how the relationship between climate and human evolution was not simply linear or deterministic. The same environmental changes could produce different evolutionary outcomes depending on the existing cultural and technological context of human populations at the time. This context dependency explains why human evolution appears to have accelerated over time rather than proceeding at a constant rate. Each major adaptive breakthrough created new possibilities for responding to environmental challenges, leading to increasingly rapid innovation cycles during periods of climate stress. The feedback loops between environmental challenges, technological innovation, social cooperation, and cognitive development created a form of evolutionary acceleration that distinguished human development from that of other species. Climate variability didn't just select for specific traits, it selected for the ability to rapidly develop new traits through cultural innovation. Understanding these feedback loops provides insight into why humans became the dominant species on Earth, despite being relatively recent arrivals in evolutionary terms. The climate-driven evolution of adaptability itself created a form of meta-adaptation that allowed humans to successfully colonize virtually every terrestrial environment on the planet. The story of climate-driven human evolution also illuminates the relationship between environmental challenges and the development of human cooperation. Many of the most distinctive aspects of human social behavior, from complex language to large-scale cooperation between non-relatives, can be traced to adaptive responses to environmental unpredictability. Climate variability created situations where individual survival strategies were insufficient, requiring coordination between multiple individuals and even multiple groups to successfully navigate environmental challenges. The social bonds and communication systems that emerged from these cooperative requirements became the foundation for increasingly complex human societies. The archaeological evidence for large-scale cooperation during periods of environmental stress includes shared resource processing sites, coordinated hunting strategies involving multiple groups, and evidence for information sharing about environmental conditions across vast distances. These cooperative behaviors required sophisticated social organization and communication abilities that went far beyond what was necessary for basic survival. But cooperation also required the development of social institutions and cultural norms that could maintain group cohesion and prevent conflicts over scarce resources during difficult periods. The emergence of ritual behaviors, symbolic marking systems, and formalized social roles during the Middle Stone Age may reflect these institutional innovations. Archaeological sites from this period show evidence for increasingly elaborate symbolic behaviors that serve to reinforce group identity and social bonds. Complex geometric engravings, standardized tool decorations, and ritual burial practices all point to the development of cultural systems designed to maintain social cooperation under stress. These cultural innovations represent another form of climate-driven adaptation, addressing the social challenges created by environmental unpredictability rather than just the immediate survival challenges. The development of institutions capable of maintaining cooperation during resource scarcity became as important for human survival as any technological innovation. The relationship between climate stress and institutional innovation continues to characterize human societies today, suggesting that this represents a fundamental pattern in human cultural evolution. Environmental challenges consistently drive the development of new forms of social organization and cooperation that enhance collective survival prospects. But the story of climate-driven human evolution also reveals the importance of environmental diversity in driving innovation. Some of the most significant advances in human technology and culture occurred in regions characterized by high spatial and temporal environmental variability rather than simply harsh conditions. The East African Rift Valley, which served as the primary theatre for early human evolution, was characterized not just by climate instability, but by extraordinary environmental diversity within relatively small geographic areas. Volcanic activity, tectonic processes, and complex topography created a mosaic of different microenvironments that changed rapidly both spatially and temporally. This environmental heterogeneity meant that human populations could experience multiple different environmental challenges within short distances and time periods. The adaptive solutions developed for one environment could be tested and modified for application in different conditions, accelerating the pace of innovation and cultural development. Archaeological evidence from the Rift Valley shows that human populations during periods of maximum environmental diversity developed more sophisticated and varied toolkits than populations in more homogeneous environments. The diversity of environmental challenges drove the development of diverse technological solutions that provided greater overall adaptability. The principle of environmental diversity driving innovation appears to have operated at multiple scales throughout human evolutionary history. Regions with high environmental variability consistently produced more technological innovations than more stable areas, and populations that experienced diverse environmental challenges developed more flexible adaptive strategies. This relationship between environmental diversity and innovation suggests that climate-driven human evolution was not simply about surviving environmental stress, but about developing the cognitive and cultural abilities necessary to thrive in an unpredictable and diverse world. Environmental challenges became opportunities for developing new forms of adaptability rather than just obstacles to be overcome. The implications of this understanding extend beyond evolutionary history to contemporary questions about human adaptability and resilience. The climate-driven evolution of human flexibility and innovation provides a foundation for understanding how our species might respond to future environmental challenges, including anthropogenic climate change. The same cognitive and cultural abilities that allowed our ancestors to survive ice ages, volcanic eruptions, and dramatic ecosystem transformations remain fundamental characteristics of human societies today. Understanding how these abilities evolved provides insight into their potential applications for addressing contemporary environmental challenges. However, the relationship between environmental challenges and human innovation is not automatically beneficial. The archaeological record also shows examples of human populations that failed to adapt successfully to environmental changes, leading to cultural collapse or population extinction in specific regions. The factors that determine success or failure in adapting to environmental challenges appear to be related to the existing cultural and technological context of populations when challenges arose, the severity and speed of environmental changes, and the availability of alternative strategies and resources through social networks. Populations with diverse technological repertoires, strong social cooperation, and extensive trade networks were more likely to successfully navigate environmental challenges than those with more limited adaptive resources. This suggests that building adaptive capacity before crises occur is crucial for successful environmental adaptation. The study of climate-driven human evolution thus provides both inspiration and warning about human adaptability. While our species has demonstrated remarkable resilience and innovation in response to environmental challenges throughout its history, success was not inevitable and required specific cultural and social conditions that needed to be actively maintained and developed. The relationship between climate variability and human cultural evolution also reveals the importance of preserving cultural diversity as a form of adaptive insurance against future environmental uncertainty. Just as genetic diversity provides populations with greater evolutionary potential, cultural diversity provides human societies with a broader range of potential solutions to environmental challenges. The loss of cultural knowledge and traditional adaptive strategies represents a reduction in humanity's collective capacity to respond to environmental changes, even when these traditional strategies might seem irrelevant to contemporary conditions. Many traditional societies developed sophisticated understanding of environmental patterns and sustainable resource management practices that required generations to develop and could be lost within a few decades. Preserving and understanding this cultural diversity is not just a matter of historical interest, but a practical necessity for maintaining human adaptability in an uncertain future. The climate-driven evolution of human culture created a vast repository of knowledge about environmental adaptation that remains relevant for contemporary challenges. The archaeological record of climate-driven innovation also demonstrates the importance of experimental approaches to environmental adaptation. Many of the most successful innovations in human history emerged through trial and error processes that involved multiple failed attempts before successful solutions were developed. Archaeological sites often show evidence for technological experimentation and innovation attempts that were ultimately abandoned in favor of more successful approaches. This pattern of experimentation and selection appears to have been crucial for developing the successful adaptive strategies that characterize human societies. The willingness to experiment with new approaches, even at the risk of failure, may itself be one of the most important adaptations that emerged from climate-driven human evolution. Environmental unpredictability selected for cognitive and cultural flexibility that encouraged innovation rather than rigid adherence to traditional approaches. This experimental orientation toward environmental challenges distinguishes human adaptation from that of most other species, which tend to rely primarily on genetically encoded behavioral programs. The cultural evolution of experimental approaches to problem solving provided humans with unprecedented adaptability to novel environmental conditions. But experimental adaptation also requires social and cultural institutions capable of preserving and transmitting knowledge about both successful and unsuccessful strategies. The development of sophisticated systems for cultural transmission and knowledge preservation was therefore as important as the innovations themselves. Archaeological evidence for increasingly complex symbolic communication systems during periods of environmental stress may reflect the development of these knowledge preservation and transmission capabilities. The ability to encode, store, and retrieve information about environmental patterns and adaptive strategies became crucial for maintaining cultural adaptations across generations. The relationship between climate-driven innovation and cultural transmission systems reveals another important aspect of human environmental adaptation. Unlike genetic adaptations, which are automatically inherited by offspring, cultural adaptations must be actively learned and transmitted through social processes that can be disrupted by environmental or social changes. Maintaining cultural adaptations therefore requires not just developing successful strategies, but also maintaining the social institutions and communication systems necessary for transmitting these strategies to future generations. Environmental challenges that disrupted social organization could lead to the loss of crucial adaptive knowledge, even when the knowledge itself remained relevant. The archaeological record shows several examples of apparent technological regression in human populations following periods of social disruption, suggesting that maintaining cultural adaptations required continuous investment in education and knowledge transmission systems. Environmental adaptation was therefore not just a matter of developing solutions, but of maintaining the cultural capacity to preserve and apply these solutions over time. Understanding the relationship between environmental challenges, innovation, and cultural transmission provides insight into the conditions necessary for successful long-term adaptation to environmental change. Technical solutions alone are insufficient without the social and cultural infrastructure necessary to implement and maintain them effectively. The climate-driven evolution of human societies thus involved not just the development of new technologies and strategies, but the co-evolution of social institutions capable of supporting and maintaining these adaptations. The most successful human populations were those that developed integrated systems, linking technological innovation, social cooperation, and cultural transmission. These integrated adaptive systems allowed human societies to accumulate knowledge and capabilities over time, rather than having to redevelop solutions to recurring challenges with each generation. The cumulative nature of cultural evolution distinguished human environmental adaptation from that of other species and enabled the development of increasingly sophisticated responses to environmental challenges. The archaeological evidence for accelerating innovation rates over time reflects this cumulative aspect of human cultural evolution. Each major adaptive breakthrough provided a foundation for further innovations, leading to exponential rather than linear increases in human adaptive capabilities. This acceleration of adaptive capacity may explain why human environmental impact has grown so dramatically in recent millennia, despite the relatively recent origin of our species. The cumulative effects of climate-driven cultural evolution created unprecedented capabilities for environmental modification and resource exploitation. However, the same processes that enabled human environmental dominance also created new forms of environmental challenge that may require different adaptive approaches than those that characterized earlier periods of human evolution. Understanding the relationship between climate-driven adaptation and environmental impact provides crucial context for addressing contemporary environmental challenges. The study of climate-driven human evolution thus offers both historical perspective and practical guidance for navigating current and future environmental changes. The deep history of human environmental adaptation provides a foundation for understanding both the potential and the limitations of human adaptability in the face of unprecedented global environmental change. Environmental change. The story we've been unraveling takes another fascinating turn when we examine how these ancient climate pressures didn't just shape individual human traits, but fundamentally rewired how our species thinks about problems themselves. Around 300,000 years ago, something unprecedented began appearing in the archaeological record of Africa. Tools that had no immediate practical purpose. Objects that seemed designed not for cutting, hunting, or processing food, but for something entirely different. These were the first clear signs of abstract thinking, and their timing coincides perfectly with some of the most dramatic climate fluctuations in African geological history. Ochre pigments ground into powder for body decoration. Geometric engravings carved into stones with no utilitarian function. Shell beads perforated and worn as ornaments, sometimes transported hundreds of kilometers from their marine sources. To understand why this matters, you need to grasp what abstract thinking actually represents in evolutionary terms. When an early human spent precious time and energy creating a geometric pattern on a piece of ochre, they were demonstrating cognitive abilities that had never existed before in the history of life on Earth. They were manipulating symbols, creating representations of ideas rather than just tools for immediate survival needs. This wasn't art for art's sake. These symbolic behaviors served crucial adaptive functions in societies facing unprecedented environmental challenges. Body decoration using ochre pigments likely served as a form of group identification, allowing individuals to quickly recognize members of their own social network during periods when different groups might compete for scarce resources. The geometric engravings found at sites across Africa from this period show remarkable consistency in their patterns, suggesting shared symbolic systems that could communicate complex information across time and space. These weren't random doodles. They were information storage and transmission systems that allowed human groups to preserve and share crucial knowledge about environmental patterns, resource locations, and survival strategies. But the development of symbolic thinking had implications that extended far beyond immediate survival needs. The ability to manipulate abstract concepts in the mind created new possibilities for planning, problem-solving, and innovation that transformed how humans approached environmental challenges. Consider what symbolic thinking allows that concrete thinking cannot achieve. With symbolic thinking, you can mentally model different possible futures and evaluate potential outcomes before committing to specific actions. You can represent abstract relationships between different environmental variables and use these models to predict how changes in one factor might affect others. Most importantly, symbolic thinking allows you to communicate complex, abstract information to other individuals, enabling forms of cooperation and coordination that would be impossible with concrete communication alone. You can share not just information about current conditions, but plans for future actions, hypothetical scenarios, and abstract principles that can be applied across multiple different situations. The archaeological evidence suggests that these symbolic thinking capabilities emerged specifically in response to environmental challenges that required increasingly complex forms of planning and coordination. Sites dating to periods of maximum climate instability show the highest concentrations of symbolic artifacts, indicating that abstract thinking was most adaptive when environmental conditions were most unpredictable. This relationship between environmental uncertainty and cognitive innovation reveals something profound about how human intelligence evolved. Rather than developing as a general-purpose problem-solving capability, human abstract thinking appears to have evolved specifically as an adaptation to environmental unpredictability. The cognitive abilities that allow humans to engage in scientific reasoning, mathematical thinking, and artistic creation all trace back to these early adaptations for navigating uncertain environments. The mental flexibility required to survive in rapidly changing ecological conditions provided the foundation for all subsequent human intellectual achievements. But symbolic thinking also enabled something that would prove even more transformative for human evolution. It made possible the development of cumulative culture, where knowledge and innovations could be preserved, modified, and built upon across generations rather than being lost when their original creators died. Archaeological evidence from sites across Africa shows that technological innovations began persisting and spreading much more rapidly after the emergence of symbolic communication systems. Tool technologies that had previously been restricted to specific regions and time periods began appearing across vast distances, indicating that information about their creation and use was being transmitted through symbolic communication networks. This cultural transmission wasn't just simple imitation. The archaeological record shows evidence for systematic modification and improvement of technologies as they spread, indicating that symbolic communication allowed not just preservation of existing knowledge, but active innovation and development of new capabilities. The emergence of cumulative culture represents one of the most significant transitions in evolutionary history. For the first time, a species had developed the ability to accumulate knowledge and capabilities faster than they could be lost through individual death or environmental disruption. Human societies could become more sophisticated over time rather than simply maintaining existing capabilities. This transition from individual to cumulative adaptation fundamentally changed the relationship between humans and their environment. Instead of each generation having to independently develop solutions to environmental challenges, human societies could build upon the innovations of previous generations, leading to exponentially increasing adaptive capabilities. The effects of this transition become apparent in the archaeological record through accelerating rates of technological innovation and increasing sophistication of tool technologies over time. Middle Stone Age sites show progressively more complex and diverse toolkits, indicating that cumulative cultural evolution was driving technological advancement at unprecedented rates. But cumulative culture also created new vulnerabilities that hadn't existed in earlier human societies. Cultural knowledge could be lost through social disruption, population decline, or breakdown of transmission systems, potentially leading to technological regression rather than continued advancement. Archaeological sites from periods of environmental stress show evidence for both technological innovation and technological loss, indicating that the relationship between environmental challenges and cultural evolution was complex and not always beneficial. Environmental conditions that promoted innovation in some contexts could lead to cultural collapse in others. The factors that determined whether environmental challenges led to innovation or collapse appear to be related to the existing social and technological context of human populations when challenges arose. Societies with robust cultural transmission systems, diverse technological repertoires, and extensive social networks were more likely to respond to environmental stress with innovation rather than regression. This observation has important implications for understanding human adaptability more generally. The capacity for cumulative cultural evolution that emerged during the Middle Stone Age provided humans with unprecedented adaptive potential, but realizing this potential required maintaining specific social and cultural conditions that could themselves be disrupted by environmental changes. The relationship between environmental challenges and cultural evolution thus involved complex feedback loops between technological innovation, social organization, and environmental adaptation that could produce either positive or negative outcomes depending on specific circumstances. Understanding these feedback loops provides insight into why some human societies have been more successful than others at adapting to environmental changes throughout history. Success appears to depend not just on having appropriate technologies or social institutions, but on maintaining integrated systems that can preserve and build upon adaptive knowledge over time. The archaeological record of climate-driven human evolution also reveals the crucial importance of population size and density in driving innovation and cultural evolution. Regions with larger and more interconnected human populations consistently show higher rates of technological innovation than areas with smaller or more isolated groups. This relationship between population parameters and innovation rates appears to reflect the statistical properties of cultural transmission and innovation processes. Larger populations provide more opportunities for innovation to occur through individual experimentation and creativity. More importantly, they also provide better conditions for preserving and spreading innovations once they occur. Mathematical models of cultural evolution show that innovation rates depend critically on the balance between innovation and loss rates in populations. Small or isolated populations tend to lose cultural knowledge faster than they can develop new innovations, leading to technological stagnation or regression over time. Large, interconnected populations can maintain higher levels of cultural complexity because they have sufficient capacity to preserve existing knowledge while simultaneously developing new innovations. The relationship between population size and cultural complexity appears to be one of the fundamental principles governing human cultural evolution. Archaeological evidence from Africa during the Middle Stone Age supports these theoretical predictions. Regions with higher population densities and more extensive trade networks show more diverse and sophisticated technological repertoires than areas with smaller or more isolated populations. The implications extend beyond technological innovation to other aspects of cultural evolution, including social institutions, symbolic systems, and environmental management practices. All forms of cultural knowledge appear to be subject to similar population-dependent transmission and loss processes. This understanding provides important context for interpreting the relationship between climate change and human cultural evolution. Environmental changes that affected population sizes or connectivity between groups would have had cascading effects on cultural evolution rates and directions that might be more important than their direct effects on survival and resource availability. Climate-driven population bottlenecks could lead to significant cultural losses even when populations successfully survived environmental challenges from a biological perspective. Conversely, environmental changes that promoted population growth and connectivity could accelerate cultural evolution even when they created new survival challenges. The archaeological record shows several examples of apparent cultural regression following periods of population decline, even when the populations involved had previously demonstrated sophisticated technological capabilities. This pattern suggests that maintaining cultural complexity requires continuous investment in population growth and social connectivity. Understanding the relationship between population dynamics and cultural evolution also provides insight into the geographic patterns of human innovation and adaptation throughout history. Regions that maintained large interconnected populations consistently served as centers of innovation that influenced technological and cultural development across much wider areas. The African continent served this role during the early stages of human evolution, providing the population base and environmental challenges necessary for driving the initial development of human cultural capabilities. Later centers of innovation in Asia, Europe, and the Americas built upon this foundation, while developing their own regional specializations. The pattern of innovation centers, connected by trade and communication networks, appears to be a fundamental feature of human cultural evolution that emerged during the climate-driven developments of the Middle Stone Age. These networks provided the population connectivity necessary for maintaining and advancing cultural complexity while allowing regional adaptation to local environmental conditions. But the story of climate-driven human evolution takes another crucial turn when we examine how environmental challenges affected the development of human cooperation and social organization. The archaeological evidence reveals that periods of environmental stress consistently coincided with innovations in social technology that were just as important as advances in material technology. Rock art sites across Africa from the Middle Stone Age show increasingly sophisticated depictions of group activities, including coordinated hunting, ritual gatherings, and symbolic ceremonies that appear designed to reinforce social bonds and group identity. These artistic representations provide direct evidence for the development of complex social institutions during periods of environmental challenge. The timing of these social innovations corresponds precisely with periods of maximum climate variability, suggesting that environmental uncertainty drove the development of new forms of social organization just as it drove technological innovation. Groups that could maintain cooperation and coordination during environmental stress had significant survival advantages over those that couldn't. Archaeological evidence for large-scale cooperative activities during this period includes shared resource processing sites, where multiple groups appear to have collaborated in processing large game animals or plant resources. These sites show evidence for standardized processing techniques and equitable distribution of resources that indicate sophisticated social institutions for managing cooperation. The development of these cooperative institutions required solving complex social problems related to resource sharing, conflict resolution, and coordination of group activities. Archaeological sites show evidence for increasingly elaborate symbolic systems that appear to have served these social functions. Standardized symbolic markers found at sites across vast distances suggest the development of shared identity systems that could facilitate cooperation between groups that might not have direct kinship relationships. These symbolic systems provided a foundation for the large-scale cooperative networks that characterize human societies. The archaeological record also shows evidence for increasingly complex burial practices during periods of environmental stress, indicating the development of ritual systems designed to reinforce social bonds and group cohesion. These practices required significant investment of time and resources that would only have been adaptive if they provided substantial benefits for group survival. Ritual behaviors serve multiple functions in human societies, including reinforcing cooperation, transmitting cultural knowledge, and maintaining group identity during periods of stress. The development of increasingly elaborate ritual systems during periods of environmental challenge suggests that these functions became more important when environmental conditions were unstable. The emergence of complex ritual behaviors during the Middle Stone Age provides direct evidence for the co-evolution of environmental adaptation and social complexity in human societies. Environmental challenges didn't just drive technological innovation, they drove the development of the social institutions necessary for implementing and maintaining technological solutions. This co-evolutionary relationship between environmental adaptation and social complexity appears to be one of the distinguishing features of human evolution. Other species developed technological capabilities for environmental adaptation, but humans uniquely developed integrated technological and social systems that could be maintained and improved over time through cultural evolution. The archaeological evidence suggests that this integration of technological and social innovation was crucial for human success in adapting to environmental challenges. Populations that developed sophisticated technologies without corresponding social institutions for maintaining and transmitting them were less successful than those that developed integrated socio-technological systems. Understanding this relationship provides insight into why human societies became so much more complex than those of other species despite sharing similar environmental challenges. The ability to develop and maintain integrated technological and social systems provided humans with adaptive capabilities that no other species could match. But the development of complex social institutions also created new challenges that had to be addressed through further innovation. Managing cooperation in large groups requires sophisticated systems for communication, decision-making, and conflict resolution that become increasingly complex as group sizes and interaction networks grow. Archaeological evidence from the later Middle Stone Age shows increasingly sophisticated symbolic communication systems that appear designed to address these social challenges. Standardized symbolic markers, complex geometric patterns, and elaborate decorative systems all indicate the development of communication technologies for managing social complexity. These symbolic communication systems served functions analogous to those of written language in later human societies, allowing the preservation and transmission of complex social and cultural information across time and space. The development of these systems during periods of environmental stress suggests that they were crucial adaptations for maintaining social cooperation under challenging conditions. The relationship between environmental challenges and social innovation thus created a positive feedback loop where environmental stress drove social complexity which enabled more effective environmental adaptation, which supported larger and more complex societies, which could develop even more sophisticated adaptive strategies. This feedback loop appears to be one of the key mechanisms driving the acceleration of human cultural evolution over time. Each cycle of environmental challenge and social innovation created new capabilities that could be applied to subsequent challenges, leading to exponentially increasing adaptive potential. The archaeological record shows clear evidence for this acceleration, with innovation rates and cultural complexity increasing dramatically over time rather than remaining constant. The pace of change during the later Middle Stone Age far exceeded that of earlier periods, indicating that cumulative cultural evolution was creating exponential rather than linear growth in human capabilities. Understanding these acceleration dynamics provides crucial context for interpreting contemporary human adaptability and environmental impact. The same processes that enabled human success in adapting to ancient climate changes also created the technological and social capabilities that now allow humans to modify global environmental systems. The relationship between ancient climate-driven innovation and contemporary environmental challenges thus involves complex continuities and discontinuities that require careful analysis. The adaptive capabilities that evolved in response to natural climate variability may or may not be adequate for addressing anthropogenic environmental changes that differ in scale, speed, and character from those that shaped human evolution. But examining how environmental challenges drove innovation and adaptation throughout human evolutionary history provides valuable insights into the potential and limitations of human adaptability more generally. The deep history of climate-driven human evolution offers both inspiration and guidance for addressing contemporary environmental challenges. The story becomes even more intricate when we examine how climate-driven human evolution affected the development of human spatial cognition and navigation abilities. Archaeological evidence from the Middle Stone Age reveals that human populations were traveling over increasingly vast distances to obtain resources, maintain social relationships, and explore new territories. Stone tools found at archaeological sites often originated from raw material sources located hundreds of kilometers away, indicating that Middle Stone Age humans were either traveling enormous distances themselves or participating in trade networks that spanned entire continents. Either possibility requires sophisticated spatial cognition and navigation abilities that far exceed those of other species. The development of these enhanced spatial abilities appears to be directly related to the environmental challenges created by climate variability. When local resources became unreliable due to environmental changes, survival often depended on knowledge of alternative resource locations across vast landscapes. Maintaining mental maps of resource locations, seasonal availability patterns, and travel routes across hundreds of thousands of square kilometers requires cognitive capabilities that are fundamentally different from those needed for local resource exploitation. These capabilities had to be learned, maintained, and transmitted through cultural systems that could preserve spatial knowledge across generations. Archaeological evidence suggests that the development of these spatial cognition systems was closely linked to the emergence of symbolic communication and abstract thinking capabilities. Complex spatial information could only be effectively transmitted through symbolic systems capable of representing abstract relationships between geographic features, temporal patterns, and resource availability. Rock art sites from the Middle Stone Age often include what appear to be map-like representations of landscape features, travel routes, and resource locations. These symbolic maps provided a means for preserving and transmitting crucial spatial knowledge that could be accessed by future generations or shared with other groups. The development of symbolic mapping systems represents another form of environmental adaptation that emerged in response to climate-driven resource uncertainty. When local knowledge was insufficient for survival, human societies developed cultural technologies for preserving and accessing spatial knowledge from much larger geographic areas. These mapping systems also enabled new forms of social cooperation and resource sharing that wouldn't have been possible without accurate spatial information. Groups could coordinate resource use across vast territories, share information about environmental conditions in distant areas, and plan cooperative activities that involved multiple groups across large geographic areas. The archaeological record shows evidence for increasingly sophisticated spatial information systems throughout the Middle Stone Age, indicating that environmental challenges continue to drive innovation in spatial cognition and navigation technologies. Human societies became progressively better at acquiring, processing, and utilizing spatial information from larger and more complex environments. This enhanced spatial cognition provided the foundation for the remarkable geographic expansion of human populations during the later Pleistocene. The ability to navigate accurately across unfamiliar territories, locate resources in new environments, and maintain spatial knowledge of vast geographic areas enabled humans to successfully colonize virtually every terrestrial environment on Earth. The speed and success of human geographic expansion during this period was unprecedented in evolutionary history and directly reflects the spatial cognition capabilities that evolved in response to climate variability in Africa. Environmental challenges that required enhanced spatial abilities for survival in African environments provided the cognitive foundation for global human expansion. But enhanced spatial cognition also had implications for other aspects of human cultural evolution beyond navigation and resource location. The mental capabilities required for processing complex spatial information also support abstract reasoning, mathematical thinking, and technological innovation in ways that may not be immediately obvious. Archaeological evidence suggests that the same cognitive systems that enabled sophisticated spatial navigation also supported the development of complex tool technologies, abstract symbolic systems, and mathematical concepts. The mental ability to manipulate spatial relationships in the mind provides a foundation for many other forms of abstract thinking. Understanding the relationship between spatial cognition and other cognitive abilities provides insight into how environmental challenges drove the integrated development of human intellectual capabilities. Climate-driven spatial challenges didn't just enhance navigation abilities. They contributed to the evolution of general intelligence capabilities that support human cultural achievements across multiple domains. The archaeological record shows that populations with more sophisticated spatial cognition systems also tended to develop more advanced technologies, more complex social organizations, and more elaborate symbolic systems. These correlations suggest that spatial cognition served as a foundation for broader cultural evolution. This relationship between spatial cognition and cultural complexity appears to reflect the integrated nature of human cognitive evolution. Environmental challenges that enhanced specific cognitive abilities had cascading effects on other mental capabilities that supported broader cultural innovation and adaptation. The development of enhanced spatial cognition during the Middle Stone Age thus represents not just an adaptation to specific environmental challenges, but a foundation for the general intellectual capabilities that distinguish human cognition from that of other species. Climate-driven cognitive evolution created mental capabilities that could be applied to challenges far beyond those that originally selected for them. Understanding this relationship provides important insights into the nature of human intelligence and its evolutionary origins. Many of the cognitive abilities that seem most distinctively human may have evolved initially as adaptations to environmental challenges that no longer exist, but persist because they provide general advantages for cultural learning and innovation. The story of climate-driven spatial cognition evolution also illustrates how environmental challenges can have unexpected consequences that extend far beyond their immediate adaptive context. Environmental pressures that required enhanced navigation abilities ultimately contributed to the evolution of the mathematical, scientific, and artistic capabilities that characterize human culture. This pattern of environmental adaptation, leading to general cognitive enhancement, appears to be a recurring theme throughout human evolutionary history. Specific environmental challenges consistently drove the development of cognitive capabilities that proved useful for addressing much broader ranges of problems and opportunities. The archaeological evidence for climate-driven cognitive evolution thus provides a foundation for understanding human intellectual potential and its relationship to environmental challenges. The same processes that enhanced human spatial cognition in response to ancient climate variability continue to operate today, suggesting that environmental challenges may continue to drive human cognitive evolution. But the relationship between environmental challenges and cognitive evolution also raises important questions about the conditions necessary for continued human intellectual development. The environmental challenges that drove ancient cognitive evolution occurred in contexts very different from contemporary human societies. Understanding how environmental challenges can promote rather than inhibit cognitive development requires careful analysis of the specific conditions that make environmental stress adaptive rather than simply destructive. The archaeological record suggests that moderate, variable challenges tend to promote cognitive development, while extreme or chronic stress tends to be maladaptive. This observation has important implications for contemporary educational and social policies aimed at promoting human intellectual development. Environmental challenges that promote cognitive growth must be carefully calibrated to provide appropriate levels of stimulation without overwhelming adaptive capabilities. The study of ancient climate-driven cognitive evolution thus offers both historical perspective and practical guidance for understanding and enhancing human intellectual potential. The deep history of human cognitive adaptation provides a foundation for developing more effective approaches to education, innovation, and intellectual development in contemporary contexts. Moving deeper into our exploration, the relationship between climate and human evolution reveals even more remarkable adaptations when we examine how environmental challenges affected human dietary strategies and nutritional physiology. The archaeological record shows that Middle Stone Age humans developed unprecedented dietary flexibility that allowed them to extract nutrition from resources that had never been exploited by earlier hominins. Sites from this period show evidence for systematic processing of marine shellfish, underground tubers, small game animals, aquatic birds, and seasonal plant resources that required sophisticated extraction and processing techniques. This dietary diversification wasn't simply opportunistic exploitation of available resources. It represented a systematic expansion of the human dietary niche that required significant technological and cultural innovation. The development of these diverse dietary strategies appears to be directly linked to climate-driven environmental variability that made traditional food sources unreliable. When large game animals or preferred plant resources became scarce due to environmental changes, human survival depended on the ability to quickly shift to alternative food sources that might require completely different procurement and processing techniques. Archaeological evidence shows that human dietary strategies became increasingly sophisticated throughout the Middle Stone Age, with later sites showing exploitation of resources that would have been impossible to utilize without advanced processing technologies. Underground tubers, for example, often require elaborate preparation techniques to remove toxins and make nutrients accessible. The development of cooking technologies played a crucial role in this dietary expansion. Fire-based processing techniques allowed humans to access nutrients from resources that would have been inedible or nutritionally inadequate without thermal processing. Cooking also improved the digestibility of many foods, increasing the caloric return from dietary investments. But dietary diversification also required sophisticated ecological knowledge about resource availability, seasonal patterns, and optimal harvesting techniques. Exploiting diverse food resources effectively requires understanding complex relationships between environmental conditions and resource productivity that can only be acquired through extensive experience and cultural transmission. Archaeological sites show evidence for increasingly systematic resource processing activities that indicate the development of specialized knowledge about optimal harvesting times, processing techniques, and storage methods for diverse food resources. This ecological knowledge had to be learned, maintained, and transmitted through cultural systems that could preserve crucial dietary information across generations. The development of diverse dietary strategies also had important nutritional consequences that affected human physiology and health. Access to diverse food resources provided more balanced nutrition and reduced the risks associated with dependence on single food sources that might become unavailable due to environmental changes. Archaeological evidence suggests that Middle Stone Age populations with more diverse dietary strategies also had better health outcomes and more stable population sizes than groups with more restricted diets. Dietary flexibility appears to have been a crucial adaptation for maintaining population viability during periods of environmental stress. The nutritional benefits of dietary diversification also supported the high metabolic demands of larger brains and more active lifestyles that characterized Middle Stone Age humans. Brain tissue requires enormous amounts of energy to develop and maintain, and diverse, high-quality diets were essential for supporting the cognitive capabilities that distinguished human evolution. The relationship between dietary innovation and cognitive evolution thus involved positive feedback loops, where enhanced cognitive abilities enabled more sophisticated dietary strategies, which provided better nutrition for supporting further cognitive development. Environmental challenges that required dietary innovation drove both nutritional and cognitive improvements. Archaeological evidence shows that populations with more sophisticated dietary technologies also tended to develop more advanced tool technologies, more complex social organizations, and more elaborate symbolic systems. These correlations suggest that dietary innovation served as a foundation for broader cultural evolution. Understanding the relationship between dietary strategies and cultural evolution provides insight into how environmental challenges can have cascading effects across multiple aspects of human adaptation. Climate-driven dietary challenges didn't just affect nutrition. They influenced technological innovation, social organization, and cognitive development in ways that shaped the entire trajectory of human cultural evolution. The archaeological record of dietary innovation also reveals the importance of experimentation and risk-taking in human environmental adaptation. Many of the dietary strategies that proved crucial for human survival required initial experimentation with resources that might have been dangerous or nutritionally inadequate. Archaeological sites show evidence for systematic experimentation with new food processing techniques, including controlled burning, fermentation, and mechanical processing methods that required significant investment of time and energy before their benefits became apparent. This experimental approach to dietary innovation required cognitive and cultural capabilities that distinguished human adaptation from that of other species. The willingness to experiment with new dietary strategies, even at considerable risk, appears to have been crucial for developing the dietary flexibility that enabled human survival during environmental challenges. Populations that were more conservative in their dietary strategies were less successful at adapting to environmental changes. This experimental orientation toward dietary challenges illustrates a broader pattern in human environmental adaptation, where innovation and risk-taking consistently provided advantages over conservative strategies. Environmental unpredictability selected for cognitive and cultural flexibility that encouraged experimentation rather than rigid adherence to traditional approaches. The development of experimental approaches to dietary challenges during the Middle Stone Age provided a foundation for the continued dietary innovation that has characterized human societies throughout history. The same cognitive and cultural capabilities that enabled ancient dietary experimentation continue to drive contemporary food production and nutritional science. Understanding the evolutionary origins of human dietary flexibility also provides insight into contemporary nutritional challenges and opportunities. The dietary adaptations that evolved in response to ancient environmental variability continue to influence human nutritional physiology and food preferences today. The archaeological record suggests that human nutritional systems evolved to function optimally with diverse variable diets, rather than consistent standardized nutrition sources. This evolutionary heritage may have important implications for understanding contemporary nutritional requirements and developing optimal dietary strategies. But the relationship between ancient dietary evolution and contemporary nutrition also involves complex interactions between evolved physiological systems and modern food environments that may require careful analysis. Nutritional systems that evolved in response to ancient environmental challenges may not be optimally adapted to contemporary dietary conditions. The study of climate-driven dietary evolution thus offers both historical perspective and practical guidance for understanding human nutritional requirements and developing effective nutritional strategies. The deep history of human dietary adaptation provides a foundation for addressing contemporary nutritional challenges while respecting the evolutionary heritage of human nutritional physiology. The story takes yet another fascinating dimension when we examine how climate-driven evolution affected human sleep patterns, circadian rhythms, and adaptation to different photoperiods across diverse latitudes. Archaeological evidence combined with physiological studies reveals that human expansion into different climatic zones required sophisticated adaptations to varying light-dark cycles and seasonal patterns. As human populations migrated from equatorial Africa into higher latitudes during the late Middle Stone Age, they encountered dramatically different photoperiod regimens that would have challenged circadian systems evolved for relatively consistent day-night cycles. Archaeological sites in northern Africa and the Levant show evidence for cultural adaptations that appear designed to address these chronobiological challenges. Fire use patterns at higher latitude sites show systematic differences from those at equatorial locations, with evidence for more extensive artificial lighting during dark periods and more structured daily activity patterns. These cultural innovations appear to represent adaptive responses to photoperiod challenges that couldn't be addressed through rapid biological adaptation. The development of artificial lighting technologies also enabled human activities to continue during periods when natural light was insufficient, effectively extending the productive day and allowing more efficient resource utilization during short winter daylight periods. This technological adaptation to photoperiod constraints provided crucial advantages for human survival at higher latitudes. Archaeological evidence suggests that human societies at higher latitudes developed increasingly sophisticated methods for tracking seasonal changes and predicting optimal timing for various activities. Stone arrangements and carved markers found at sites across northern Africa appear to function as astronomical observation tools that could track solar and lunar cycles with remarkable precision. These astronomical tracking systems weren't just intellectual curiosities. They served crucial practical functions for populations whose survival depended on accurate timing of seasonal resource exploitation, migration patterns, and social activities. Understanding when to harvest particular resources, when to move between seasonal camps, and when to coordinate group activities became matters of life and death in environments with pronounced seasonal variation. The cognitive demands of developing and maintaining these astronomical observation systems required mathematical thinking and abstract reasoning capabilities that built upon the enhanced spatial cognition that had evolved in response to earlier environmental challenges. Climate-driven expansion into new latitudes thus continued to drive cognitive evolution in directions that enhanced human intellectual capabilities. Archaeological sites from this period show evidence for increasingly standardized measurement systems and mathematical concepts that appear to be related to astronomical observation and seasonal tracking. Stone markers with precise geometric relationships and counting systems indicate the development of mathematical technologies for managing temporal and spatial information. The relationship between astronomical observation and mathematical development reveals another way that environmental challenges drove intellectual innovation beyond their immediate adaptive context. Requirements for accurate seasonal tracking led to mathematical discoveries that could be applied to many other technological and cultural challenges. But adaptation to different photoperiods also required physiological adjustments that went beyond cultural innovations. Human populations at different latitudes show systematic differences in circadian rhythm characteristics, sleep patterns, and seasonal mood regulation that appear to reflect genetic adaptations to local light-dark cycles. These physiological adaptations developed relatively rapidly compared to most evolutionary changes, suggesting that photoperiod adaptation involves strong selective pressures and possibly genetic mechanisms that could respond quickly to environmental challenges. The speed of these adaptations indicates that climate-driven migration created intense selective environments. Archaeological evidence combined with genetic studies reveals that human populations developed diverse physiological strategies for managing circadian challenges associated with different latitudes. Some populations appear to have developed enhanced sensitivity to available light cues, while others developed more robust internal timing systems that could maintain regular rhythms despite variable external cues. The diversity of physiological strategies for photoperiod adaptation illustrates another important principle of human environmental adaptation. Instead of developing single optimal solutions to environmental challenges, human populations often evolved multiple different approaches that could be effective under different conditions. This physiological diversity provided human populations with greater collective resilience to environmental variation, while allowing regional optimization for local conditions. Populations with different circadian adaptations could potentially share territories or resources during different seasons when their activity patterns complemented rather than competed with each other. The development of diverse photoperiod adaptations also had implications for social organization and cultural practices. Populations with different circadian characteristics might naturally develop different daily activity patterns, social rhythms, and cultural practices that reflected their underlying physiological differences. Archaeological sites show evidence for systematic differences in activity timing and social organization between populations at different latitudes that appear to reflect these physiological adaptations. Daily activity patterns, meal timing, and social gathering schedules all show systematic relationships to local photoperiod characteristics. Understanding the relationship between photoperiod adaptation and cultural variation provides insight into how environmental factors can influence human social and cultural evolution through their effects on underlying physiological systems. Climate-driven physiological changes created new possibilities and constraints for cultural development. The study of photoperiod adaptation also reveals the integrated nature of human environmental adaptation involving biological, technological, and cultural innovations that work together to address environmental challenges. No single type of adaptation was sufficient. Successful photoperiod adaptation required coordinated changes across multiple systems. Archaeological evidence suggests that populations with more integrated adaptation strategies were more successful at expanding into new latitudinal zones than those that relied primarily on single approaches. The most successful human expansions involved populations that could simultaneously deploy biological, technological, and cultural adaptations. This pattern of integrated adaptation appears to be a fundamental characteristic of human environmental adaptation that distinguishes our species from others that typically rely primarily on biological adaptations. The ability to coordinate multiple different types of adaptation provided humans with unprecedented flexibility for environmental colonization. The relationship between photoperiod adaptation and human expansion also demonstrates how environmental challenges at the margins of human range could drive innovations that benefited populations across much wider areas. Adaptations developed for high-latitude survival often proved useful for populations in other environments with different but related challenges. Astronomical observation systems developed for seasonal tracking at high latitudes could be applied to agricultural timing, navigation, and social coordination in many different environments. Mathematical concepts developed for managing temporal variation proved useful for addressing spatial and technological challenges in diverse contexts. This pattern of innovation transfer from marginal to core environments appears to be another important mechanism driving human cultural evolution. Environmental challenges that pushed human adaptation to its limits consistently generated innovations that enhanced capabilities across the entire range of human environments. Understanding these innovation transfer mechanisms provides insight into how environmental diversity and expansion into challenging environments can drive technological and cultural advancement that benefits entire species. Challenging environments serve as innovation laboratories that generate solutions applicable to much broader contexts. The archaeological record shows that periods of most rapid human expansion into new environments consistently coincided with periods of most rapid technological and cultural innovation across all human populations. Expansion and innovation were mutually reinforcing processes that accelerated human cultural evolution. But photoperiod adaptation also created new forms of diversity within human populations that had important implications for social organization and cultural development. Populations adapted to different photoperiod regimens developed distinct physiological and cultural characteristics that could complement or conflict with each other during contact. Archaeological evidence shows that interactions between populations with different photoperiod adaptations sometimes led to cultural innovation and technological exchange, but could also result in social tension and conflict. Managing diversity became an increasingly important challenge as human populations expanded across diverse environments. The development of social institutions and cultural practices for managing diversity appears to be another important adaptation that emerged during periods of rapid human expansion. Populations that could successfully integrate individuals and groups with different environmental adaptations had significant advantages over those that could not. Archaeological sites show evidence for increasingly sophisticated social systems for managing cultural and physiological diversity during the later Middle Stone Age. Burial practices, artistic traditions, and settlement patterns all show adaptations for accommodating and integrating diverse populations. These social adaptations for managing diversity required enhanced communication systems, conflict resolution mechanisms, and identity management practices that built upon the symbolic thinking and social cooperation capabilities that had evolved in response to earlier environmental challenges. The relationship between environmental diversity and social complexity thus created another positive feedback loop, where expansion into diverse environments drove social innovation, which enabled more effective management of diversity, which supported further expansion and innovation. Understanding these feedback loops between environmental expansion and social development provides insight into how human societies became so much more complex than those of other species. Environmental challenges consistently drove innovations that created new possibilities for further environmental and social adaptation. The archaeological record of photoperiod adaptation also reveals the importance of maintaining connections between populations adapted to different environments. Populations that maintained trade and communication networks with groups in other environments were more successful than those that became completely isolated. Exchange of resources, technologies, and knowledge between populations adapted to different environments provided insurance against local environmental challenges, while enabling continued innovation and cultural development. Isolation typically led to technological stagnation and increased vulnerability to environmental changes. This pattern emphasizes the importance of connectivity and communication in human environmental adaptation. Successful adaptation to environmental diversity required not just local innovations, but maintenance of larger networks that could share resources and knowledge across different environments. The development of long-distance trade and communication networks during the Middle Stone Age thus represents another crucial adaptation that enabled human success in diverse environments. These networks provided the social infrastructure necessary for maintaining and expanding human environmental adaptability. Archaeological evidence shows that the most successful human populations during periods of environmental expansion were those that developed and maintained the most extensive and robust intergroup networks. Connectivity was as important as local adaptation for long-term survival and success. Understanding the relationship between connectivity and environmental adaptation provides important insights for contemporary challenges related to environmental change and human resilience. The same principles that enabled ancient human environmental success continue to be relevant for addressing modern environmental challenges. The story becomes even more remarkable when we examine how climate-driven evolution affected human vocal communication and the development of complex language capabilities. Archaeological evidence, combined with studies of modern human vocal anatomy, reveals that the environmental challenges faced during the Middle Stone Age drove innovations in communication that laid the foundation for all subsequent human linguistic achievements. The demands of coordinating complex activities across large groups during environmental challenges required communication capabilities that went far beyond the vocal signals used by other primates. Archaeological sites show evidence for increasingly sophisticated group activities that would have been impossible without complex linguistic communication. Coordinated hunting strategies involving multiple groups across large territories required the ability to share detailed information about animal behavior, environmental conditions, and tactical plans. Archaeological evidence for such coordination appears precisely during periods of maximum environmental challenge when resource procurement became most difficult. The development of projectile technologies during this period also required enhanced communication for effective use. Coordinated projectile hunting involves precise timing and positioning that can only be achieved through detailed verbal communication during the activity itself. Archaeological sites show evidence for increasingly standardized projectile technologies across vast distances, indicating that information about their construction and use was being transmitted through linguistic communication rather than simple imitation. Complex technological knowledge requires linguistic transmission for accurate preservation and modification. The emergence of symbolic artifacts during the same period provides direct evidence for the linguistic capabilities necessary to create and maintain shared symbolic systems. Geometric engravings, decorative objects, and ritual artifacts all require linguistic communication to establish and maintain their symbolic meanings. Archaeological evidence suggests that symbolic communication and complex language evolved together as integrated systems for managing the social and technological challenges created by environmental variability. Neither symbolic thinking nor complex language could have developed independently of the other. The relationship between environmental challenges and linguistic evolution reveals another way that climate-driven adaptation had consequences far beyond immediate survival needs. Communication capabilities that evolved for coordinating environmental adaptation became the foundation for all subsequent human cultural achievements. Complex language enabled human societies to accumulate and transmit cultural knowledge at unprecedented rates and scales. Linguistic communication allowed detailed preservation of technological, ecological, and social knowledge that could be accessed by future generations and shared across vast populations. The archaeological record shows accelerating rates of cultural innovation and technological development following the emergence of complex linguistic capabilities. Language appears to have been a crucial enabling technology for cumulative cultural evolution. But complex language also created new possibilities for social organization and cooperation that went far beyond those available to other species. Linguistic communication enabled forms of planning, coordination, and conflict resolution that could maintain cooperation in much larger and more diverse groups. Archaeological evidence for increasingly large and complex social gatherings during the later Middle Stone Age indicates that human societies were developing unprecedented capabilities for social organization. These large gatherings would have required sophisticated linguistic communication for coordination and management. The development of complex language also enabled new forms of knowledge specialization and division of labor that increased the efficiency and effectiveness of human environmental adaptation. Individuals could develop specialized knowledge and skills while relying on linguistic communication to access knowledge and services from other specialists. Archaeological sites show evidence for increasing specialization in tool production, resource processing, and other activities during the later Middle Stone Age. This specialization would have required linguistic communication systems for coordinating specialized activities and exchanging specialized products and services. The relationship between linguistic communication and economic specialization created another positive feedback loop where enhanced communication enabled more effective specialization, which increased productivity and innovation, which provided resources for developing even more sophisticated communication and specialization systems. Understanding these feedback loops between communication and social organization provides insight into how human societies developed the unprecedented complexity that distinguishes them from other animal societies. Linguistic communication was both a product and a driver of increasing social and technological sophistication. The archaeological record also reveals that different human populations developed distinct linguistic and cultural traditions that reflected their specific environmental adaptations. Regional variations in tool technologies, artistic traditions, and social practices indicate the development of diverse cultural and linguistic systems. This linguistic and cultural diversification provided human populations with a broader range of adaptive strategies and knowledge systems that could be drawn upon as environmental conditions changed. Diversity in communication and cultural systems served as insurance against environmental uncertainty. Archaeological evidence shows that populations with access to diverse linguistic and cultural traditions through trade and intermarriage were more successful at adapting to environmental changes than those with more homogeneous traditions. Cultural and linguistic diversity enhanced adaptive capacity. The development of mechanisms for preserving and transmitting diverse linguistic and cultural knowledge became crucial for maintaining human adaptive capacity. Archaeological sites show evidence for increasingly sophisticated systems for cultural transmission and knowledge preservation. These cultural transmission systems required not just complex language capabilities, but also social institutions and practices designed to ensure accurate preservation and transmission of crucial knowledge across generations. The development of educational and cultural practices became as important as technological innovation. Archaeological evidence suggests that populations with more robust cultural transmission systems were more resilient to environmental challenges and more successful at maintaining technological and social capabilities during difficult periods. Cultural transmission infrastructure was crucial for long-term adaptation. Understanding the relationship between cultural transmission and environmental adaptation provides insight into the conditions necessary for maintaining human adaptive capacity under environmental stress. Technical capabilities alone are insufficient without the social and cultural systems necessary to preserve and transmit them. The study of ancient linguistic and cultural evolution thus offers important lessons for contemporary challenges related to preserving and transmitting knowledge in rapidly changing environments. The same principles that enabled ancient human cultural success remain relevant for addressing modern knowledge management challenges. The relationship between linguistic evolution and environmental adaptation also reveals how communication innovations could have cascading effects across multiple aspects of human society and culture. Enhanced communication capabilities enabled innovations in technology, social organization, and cultural practices that transformed human adaptive capacity. Archaeological evidence shows that periods of most rapid linguistic and cultural innovation consistently coincided with periods of greatest environmental challenge, indicating that communication evolution was driven by adaptive pressures rather than simply emerging as a luxury during easy times. This relationship between environmental challenges and communication innovation suggests that similar pressures may continue to drive linguistic and cultural evolution today. Contemporary environmental challenges may be creating selective pressures for new forms of communication and cultural innovation. Understanding how environmental challenges drive communication evolution provides insight into the potential for continued human linguistic and cultural development. The same processes that enhanced human communication capabilities in response to ancient climate challenges may continue to operate in response to contemporary environmental changes. But the relationship between environmental challenges and communication evolution also involves complex interactions between technological, social, and linguistic innovations that require careful analysis. Communication innovations must be supported by appropriate social and technological infrastructure to be effective and sustainable. The archaeological record suggests that the most successful communication innovations were those that could be integrated with existing social and technological systems, while providing enhanced capabilities for addressing environmental challenges. Isolated communication innovations that couldn't be effectively integrated were less successful. This observation emphasizes the importance of systemic approaches to communication and cultural innovation that consider the broader social and technological context within which new communication capabilities must function. Effective innovation requires integration rather than simple addition of new capabilities. The study of ancient communication evolution thus provides both historical perspective and practical guidance for developing effective approaches to contemporary communication and cultural challenges. The deep history of human communication adaptation offers insights into the conditions and processes that enable successful communication innovation. As we delve deeper into this extraordinary story, the relationship between climate and human evolution reveals even more sophisticated adaptations. When we examine how environmental challenges affected human memory systems and information processing capabilities. The archaeological record shows that Middle Stone Age humans developed unprecedented abilities to acquire, store, and retrieve complex information that went far beyond what was necessary for immediate survival. Archaeological sites from this period show evidence for systematic organization of information about resource locations, seasonal patterns, social relationships, technological procedures, and environmental conditions that required memory capabilities far exceeding those of other species. The complexity and scale of information management evident in these sites indicates revolutionary changes in human cognitive architecture. The development of enhanced memory systems appears to be directly related to the environmental challenges created by climate variability. When environmental conditions became unpredictable, survival often depended on access to detailed information about alternative resources, backup strategies, and contingency plans that might be needed under various future scenarios. Maintaining mental databases of environmental information across multiple seasons, years, and decades required memory systems that could store, organize, and retrieve enormous amounts of detailed information. Archaeological evidence suggests that human populations developed increasingly sophisticated methods for organizing and accessing stored information. The emergence of external memory systems using symbolic markers, spatial arrangements, and artificial cues indicates that human memory capabilities were being supplemented and enhanced through technological innovations. Stone arrangements, symbolic markings, and landscape modifications all appear to function as external memory storage systems. These external memory systems weren't simple reminders or markers. Archaeological analysis reveals sophisticated organizational principles that indicate understanding of abstract relationships between different types of information. Memory technologies were being used to enhance rather than replace human cognitive capabilities. The development of enhanced memory systems also enabled new forms of learning and knowledge transmission that accelerated cultural evolution. Detailed information about environmental patterns, technological procedures, and social relationships could be preserved and shared more effectively through enhanced memory capabilities. Archaeological evidence shows that populations with more sophisticated memory and information management systems also developed more advanced technologies, more complex social organizations, and more elaborate cultural traditions. Memory enhancement appears to have been a foundation for broader cultural advancement. The relationship between memory enhancement and cultural evolution created positive feedback loops, where better information management enabled more sophisticated cultural practices, which generated more complex information that required even better memory systems for effective management. Understanding these feedback loops between cognitive capabilities and cultural complexity provides insight into how human intellectual development accelerated over time. Memory enhancement was both a product and a driver of increasing cultural sophistication. The archaeological record also reveals that different human populations developed distinct approaches to memory enhancement and information management that reflected their specific environmental and cultural contexts. Regional variations in symbolic systems and information organization indicate diverse cognitive traditions. This diversity in memory and information management strategies provided human populations with a broader range of cognitive tools that could be applied to different types of challenges. Cognitive diversity enhanced collective problem-solving capabilities. Archaeological evidence shows that populations with access to diverse memory and information management traditions through cultural exchange were more innovative and adaptable than those with more limited cognitive repertoires. Cognitive diversity was as important as technological diversity for adaptive success. The development of mechanisms for preserving and transmitting diverse cognitive strategies became crucial for maintaining human intellectual capabilities. Archaeological sites show evidence for increasingly sophisticated systems for cognitive transmission and enhancement. These cognitive transmission systems required not just individual memory capabilities, but also social institutions and cultural practices designed to preserve and share cognitive knowledge across generations. The development of educational traditions became as important as any technological innovation. Archaeological evidence suggests that populations with more robust cognitive transmission systems were more successful at maintaining and advancing intellectual capabilities during difficult periods. Cognitive infrastructure was crucial for long-term cultural development. Understanding the relationship between cognitive transmission and cultural advancement provides insight into the conditions necessary for maintaining human intellectual capacity under environmental stress. Cognitive capabilities alone are insufficient without the social and cultural systems necessary to preserve and enhance them. The study of ancient cognitive evolution thus offers important lessons for contemporary challenges related to education, knowledge management, and intellectual development. The same principles that enabled ancient cognitive advancement remain relevant for addressing modern educational and intellectual challenges. The relationship between cognitive evolution and environmental adaptation also reveals how intellectual capabilities could have effects far beyond their original adaptive context. Memory and information processing abilities that evolved for environmental challenges became the foundation for scientific, artistic, and philosophical achievements. Archaeological evidence shows that periods of most rapid cognitive innovation consistently coincided with periods of greatest environmental challenge, indicating that intellectual development was driven by adaptive pressures rather than emerging as a luxury during stable times. This relationship between environmental challenges and cognitive innovation suggests that similar pressures may continue to drive intellectual development today. Contemporary environmental challenges may be creating selective pressures for new forms of cognitive capability. Understanding how environmental challenges drive cognitive evolution provides insight into the potential for continued human intellectual advancement. The same processes that enhanced human cognitive capabilities in response to ancient climate challenges may continue to operate in response to contemporary environmental changes. But the relationship between environmental challenges and cognitive evolution also involves complex interactions between biological, technological, and cultural factors that require careful analysis. Cognitive innovations must be supported by appropriate biological and technological infrastructure to be effective and sustainable. The archaeological record suggests that the most successful cognitive innovations were those that could be integrated with existing biological and technological systems, while providing enhanced capabilities for addressing environmental challenges. Isolated cognitive capabilities that couldn't be effectively implemented were less successful. This observation emphasizes the importance of integrated approaches to cognitive enhancement that consider the broader biological and technological context within which new cognitive capabilities must function. Effective cognitive development requires systemic rather than isolated improvements. The study of ancient cognitive evolution thus provides both historical perspective and practical guidance for developing effective approaches to contemporary cognitive and educational challenges. The deep history of human cognitive adaptation offers insights into the conditions and processes that enable successful cognitive development. The story takes another fascinating turn when we examine how climate-driven evolution affected human aesthetic sensibilities and the development of artistic capabilities. Archaeological evidence from the Middle Stone Age reveals that environmental challenges drove the emergence of aesthetic behaviors that went far beyond simple decoration or status display. The earliest artistic artifacts appear precisely during periods of maximum environmental instability, suggesting that aesthetic capabilities evolved as adaptive responses to environmental challenges rather than as luxury behaviors that emerged during periods of abundance. Rock art, decorative objects, and symbolic artifacts all show systematic relationships to environmental stress. Archaeological analysis reveals that early artistic expressions often contained sophisticated information about environmental patterns, resource locations, and seasonal timing that served crucial practical functions. Aesthetic objects weren't just beautiful, they were functional information storage and transmission systems. Rock art sites across Africa show systematic relationships between artistic content and local environmental conditions. Artistic representations of animals, plants, and landscape features provide detailed ecological information that would have been crucial for survival in variable environments. The development of aesthetic information encoding systems required cognitive capabilities for abstract representation, symbolic thinking, and pattern recognition that built upon the enhanced memory and spatial cognition that had evolved in response to earlier environmental challenges. Archaeological evidence suggests that aesthetic capabilities evolved as integrated systems, combining practical information management with emotional and social functions. Art served multiple adaptive purposes simultaneously, rather than having single functions. The emotional aspects of aesthetic experience appear to have enhanced memory and learning processes that made information transmission more effective. Beautiful or emotionally engaging information was more likely to be remembered and shared accurately across generations. Archaeological sites show evidence for increasingly sophisticated aesthetic systems that combined information encoding with emotional enhancement and social bonding functions. Art became a technology for enhancing human cognitive and social capabilities. The development of aesthetic capabilities also enabled new forms of social communication and identity formation that enhanced group cohesion during environmental challenges. Artistic traditions provided mechanisms for maintaining cultural identity and social bonds under stress. Archaeological evidence shows that populations with more elaborate artistic traditions also maintained more stable social organizations and more effective cooperation during environmental challenges. Aesthetic capabilities enhance social resilience and adaptive capacity. The relationship between aesthetic development and social organization created positive feedback loops, where artistic innovation enhanced social capabilities, which provided resources for further artistic development, which enabled even more sophisticated social organization. Understanding these feedback loops between aesthetic capabilities and social development provides insight into why human societies developed such elaborate cultural traditions. Art was not decoration, but infrastructure for social and cognitive enhancement. The archaeological record also reveals that different human populations developed distinct artistic traditions that reflected their specific environmental and cultural adaptations. Regional variations in artistic styles and content indicate diverse aesthetic approaches to environmental challenges. This diversity in artistic and aesthetic traditions provided human populations with a broader range of cultural tools for addressing environmental and social challenges. Aesthetic diversity enhanced collective creativity and problem-solving capabilities. Archaeological evidence shows that populations with access to diverse artistic traditions through cultural exchange were more innovative and adaptable than those with more limited aesthetic repertoires. Aesthetic diversity was as important as technological diversity for cultural advancement. The development of mechanisms for preserving and transmitting diverse artistic knowledge became crucial for maintaining human cultural capabilities. Archaeological sites show evidence for increasingly sophisticated systems for artistic transmission and innovation. These artistic transmission systems required not just individual aesthetic capabilities, but also social institutions and cultural practices designed to preserve and enhance artistic knowledge across generations. The development of artistic traditions became as important as technological innovation. Archaeological evidence suggests that populations with more robust artistic transmission systems were more successful at maintaining and advancing cultural capabilities during difficult periods. Aesthetic infrastructure was crucial for long-term cultural development. Understanding the relationship between artistic transmission and cultural advancement provides insight into the conditions necessary for maintaining human creative capacity under environmental stress. Artistic capabilities alone are insufficient without the social and cultural systems necessary to preserve and enhance them. The study of ancient aesthetic evolution thus offers important lessons for contemporary challenges related to cultural preservation, artistic education, and creative development. The same principles that enabled ancient artistic advancement remain relevant for addressing modern cultural challenges. The relationship between aesthetic evolution and environmental adaptation also reveals how artistic capabilities could have effects far beyond their original adaptive context. Aesthetic abilities that evolved for environmental and social challenges became the foundation for all subsequent human artistic and cultural achievements. Archaeological evidence shows that periods of most rapid aesthetic innovation consistently coincided with periods of greatest environmental challenge, indicating that artistic development was driven by adaptive pressures rather than emerging as luxury behavior during stable times. This relationship between environmental challenges and aesthetic innovation suggests that similar pressures may continue to drive artistic and cultural development today. Contemporary environmental challenges may be creating selective pressures for new forms of aesthetic and cultural capability. Understanding how environmental challenges drive aesthetic evolution provides insight into the potential for continued human artistic and cultural advancement. The same processes that enhanced human aesthetic capabilities in response to ancient climate challenges may continue to operate in response to contemporary environmental changes. But the relationship between environmental challenges and aesthetic evolution also involves complex interactions between cognitive, social, and technological factors that require careful analysis. Aesthetic innovations must be supported by appropriate cognitive and social infrastructure to be effective and sustainable. The archaeological record suggests that the most successful aesthetic innovations were those that could be integrated with existing cognitive and social systems while providing enhanced capabilities for addressing environmental challenges. Isolated aesthetic capabilities that couldn't be effectively implemented were less successful. This observation emphasizes the importance of integrated approaches to aesthetic and cultural development that consider the broader cognitive and social context within which new aesthetic capabilities must function. Effective cultural development requires systemic rather than isolated improvements. The study of ancient aesthetic evolution thus provides both historical perspective and practical guidance for developing effective approaches to contemporary artistic and cultural challenges. The deep history of human aesthetic adaptation offers insights into the conditions and processes that enable successful artistic development. Moving forward in our exploration, the relationship between climate and human evolution becomes even more intricate when we examine how environmental challenges affected human mathematical thinking and quantitative reasoning capabilities. Archaeological evidence reveals that the environmental challenges of the Middle Stone Age drove the development of mathematical concepts and numerical reasoning that provided the foundation for all subsequent human mathematical achievements. The earliest evidence for mathematical thinking appears in systematic patterns found in stone tool production, spatial arrangements of archaeological materials, and geometric designs in symbolic artifacts. These patterns indicate understanding of mathematical relationships that went far beyond what was necessary for immediate practical purposes. Archaeological analysis reveals that mathematical concepts emerged initially as solutions to practical problems related to resource management, spatial navigation, and temporal tracking in variable environments. Mathematical thinking was adaptive before it became abstract. The development of counting systems appears to be directly related to the need for managing complex resource allocation and exchange relationships during periods of environmental stress. Archaeological sites show evidence for increasingly sophisticated systems for tracking quantities and managing distributions. Stone arrangements and symbolic markers from this period often show precise geometric relationships and numerical patterns that indicate understanding of mathematical concepts, including proportion, symmetry, and numerical sequences. Mathematical thinking was being applied to practical problems. The emergence of astronomical observation systems during the same period required mathematical capabilities for tracking cyclical patterns and predicting future events based on observed relationships. Mathematical thinking enabled enhanced environmental prediction and planning. Archaeological evidence suggests that mathematical concepts evolved as integrated systems combining practical calculation with abstract reasoning and pattern recognition capabilities. Mathematics served multiple adaptive functions rather than having single purposes. The development of mathematical thinking also enabled new forms of technological innovation that required quantitative precision and systematic optimization. Tool technologies from the later Middle Stone Age show evidence for mathematical optimization of design parameters. Archaeological sites show evidence for increasingly standardized measurement systems and proportional relationships in tool production that indicate mathematical approaches to technological design. Mathematics enhanced technological capabilities and innovation. The relationship between mathematical development and technological innovation created positive feedback loops, where mathematical concepts enabled more sophisticated technologies, which required more advanced mathematics, which drove further mathematical development. Understanding these feedback loops between mathematical thinking and technological development provides insight into why human technological capabilities advanced so rapidly during this period. Mathematics was both a product and a driver of technological innovation. The archaeological record also reveals that different human populations developed distinct mathematical traditions that reflected their specific environmental and technological contexts. Regional variations in measurement systems and geometric patterns indicate diverse mathematical approaches to environmental and technological challenges. This diversity in mathematical traditions provided human populations with a broader range of quantitative tools for addressing complex problems. Mathematical diversity enhanced collective analytical and problem-solving capabilities across different environments and challenges. Archaeological evidence shows that populations with access to diverse mathematical traditions through cultural exchange were more innovative and adaptable than those with more limited quantitative repertoires. Mathematical diversity was as important as any other form of cultural diversity for adaptive success. The development of mechanisms for preserving and transmitting mathematical knowledge became crucial for maintaining human technological and analytical capabilities. Archaeological sites show evidence for increasingly sophisticated systems for mathematical education and knowledge preservation. These mathematical transmission systems required not just individual numerical capabilities, but also social institutions and cultural practices designed to preserve and enhance mathematical knowledge across generations. The development of educational traditions became essential for maintaining technological advancement. Archaeological evidence suggests that populations with more robust mathematical transmission systems were more successful at maintaining and advancing technological capabilities during difficult periods. Mathematical infrastructure was crucial for long-term technological development and environmental adaptation. Understanding the relationship between mathematical transmission and technological advancement provides insight into the conditions necessary for maintaining human analytical capacity under environmental stress. Mathematical capabilities alone are insufficient without the social and cultural systems necessary to preserve and enhance them. The study of ancient mathematical evolution thus offers important lessons for contemporary challenges related to mathematical education, technological development, and analytical thinking. The same principles that enabled ancient mathematical advancement remain relevant for addressing modern analytical challenges. The relationship between mathematical evolution and environmental adaptation also reveals how quantitative capabilities could have effects far beyond their original adaptive context. Mathematical abilities that evolved for environmental and technological challenges became the foundation for scientific, engineering, and economic achievements. Archaeological evidence shows that periods of most rapid mathematical innovation consistently coincided with periods of greatest environmental challenge, indicating that quantitative development was driven by adaptive pressures rather than emerging as abstract luxury during stable times. This relationship between environmental challenges and mathematical innovation suggests that similar pressures may continue to drive quantitative and analytical development today. Contemporary environmental challenges may be creating selective pressures for new forms of mathematical and analytical capability. Understanding how environmental challenges drive mathematical evolution provides insight into the potential for continued human quantitative advancement. The same processes that enhanced human mathematical capabilities in response to ancient climate challenges may continue to operate in response to contemporary environmental changes. The archaeological record reveals another remarkable dimension of climate-driven evolution. When we examine how environmental challenges affected human risk assessment and decision-making capabilities. Sites from the Middle Stone Age show evidence for increasingly sophisticated strategies for evaluating and managing uncertainty that required advanced cognitive abilities. Archaeological analysis reveals that human populations developed systematic approaches to risk management that involved complex calculations of probability, cost-benefit analysis, and long-term planning. These decision-making capabilities went far beyond simple trial-and-error learning or instinctive responses. The development of risk assessment abilities appears to be directly related to the environmental unpredictability that characterized this period. When traditional strategies became unreliable due to climate variability, survival depended on accurate evaluation of alternative options and their associated risks and benefits. Archaeological sites show evidence for increasingly diverse technological repertoires and resource strategies that indicate systematic diversification approaches to risk management. Human populations were developing portfolio strategies for environmental uncertainty. The emergence of trade networks and resource-sharing systems during this period required sophisticated risk assessment capabilities for evaluating the reliability of trading partners and the value of different exchange relationships. Social cooperation involved complex risk calculations. Archaeological evidence suggests that risk assessment capabilities evolved as integrated systems combining environmental monitoring, social evaluation, and technological assessment. Decision-making involved multiple types of risk analysis rather than single calculations. The development of enhanced risk assessment also enabled new forms of innovation and experimentation that required accurate evaluation of potential costs and benefits before committing resources to uncertain ventures. Innovation became more systematic and efficient. Archaeological sites show evidence for increasingly sophisticated experimental approaches to technological and cultural innovation that indicate advanced understanding of risk-reward relationships. Experimentation was becoming more strategic and less random. The relationship between risk assessment development and innovation created positive feedback loops, where better risk evaluation enabled more effective experimentation, which generated better information for future risk assessment, which enabled even more sophisticated innovation. Understanding these feedback loops between risk assessment and innovation provides insight into why human technological and cultural development accelerated during periods of environmental uncertainty. Environmental challenges drove the evolution of decision-making capabilities that enhanced innovation. The archaeological record also reveals that different human populations developed distinct approaches to risk assessment and decision-making that reflected their specific environmental and cultural contexts. Regional variations in technological strategies and social organization indicate diverse risk management traditions. This diversity in risk assessment approaches provided human populations with a broader range of decision-making tools that could be applied to different types of uncertainty. Decision-making diversity enhanced collective problem-solving capabilities under various environmental conditions. Archaeological evidence shows that populations with access to diverse risk assessment traditions through cultural exchange were more successful at navigating environmental challenges than those with more limited decision-making repertoires. Risk management diversity was crucial for adaptive success. The development of mechanisms for preserving and transmitting risk assessment knowledge became essential for maintaining human adaptive capabilities. Archaeological sites show evidence for increasingly sophisticated systems for decision-making education and knowledge preservation. These decision-making transmission systems required not just individual risk assessment capabilities, but also social institutions and cultural practices designed to preserve and enhance decision-making knowledge across generations. Educational traditions became crucial for maintaining adaptive capacity. Archaeological evidence suggests that populations with more robust decision-making transmission systems were more resilient to environmental challenges and more successful at maintaining adaptive capabilities during difficult periods. Decision-making infrastructure was essential for long-term survival. Understanding the relationship between decision-making transmission and adaptive success provides insight into the conditions necessary for maintaining human adaptive capacity under environmental uncertainty. Risk assessment capabilities alone are insufficient without the social and cultural systems necessary to preserve and enhance them. The study of ancient decision-making evolution thus offers important lessons for contemporary challenges related to risk management, decision-making education, and adaptive planning. The same principles that enabled ancient decision-making advancement remain relevant for addressing modern uncertainty and risk. The relationship between decision-making evolution and environmental adaptation also reveals how risk assessment capabilities could have effects far beyond their original adaptive context. Decision-making abilities that evolved for environmental challenges became the foundation for economic, political, and social achievements. Archaeological evidence shows that periods of most rapid decision-making innovation consistently coincided with periods of greatest environmental uncertainty, indicating that risk assessment development was driven by adaptive pressures rather than emerging during periods of stability. This relationship between environmental uncertainty and decision-making innovation suggests that similar pressures may continue to drive risk assessment and decision-making development today. Contemporary environmental challenges may be creating selective pressures for new forms of decision-making capability. Understanding how environmental challenges drive decision-making evolution provides insight into the potential for continued human adaptive advancement. The same processes that enhanced human decision-making capabilities in response to ancient climate challenges may continue to operate in response to contemporary environmental changes. The story becomes even more fascinating when we examine how climate-driven evolution affected human emotional regulation and psychological resilience capabilities. Archaeological evidence combined with studies of modern human psychology reveals that environmental challenges drove the development of emotional management systems that were crucial for survival under stress. Archaeological sites from periods of environmental instability show evidence for increasingly sophisticated social and cultural practices that appear designed to manage stress, maintain morale, and preserve psychological well-being during difficult periods. These practices indicate advanced understanding of psychological factors in survival. The development of ritual behaviors, artistic expression, and symbolic communication during periods of environmental stress appears to serve important psychological functions beyond their practical and social benefits. These activities helped maintain mental health and emotional stability under challenging conditions. Archaeological analysis reveals that human populations developed systematic approaches to stress management that involved community support systems, emotional expression opportunities, and meaning-making activities that helped individuals cope with uncertainty and hardship. The emergence of burial practices and memorial activities during this period indicates developing concepts of continuity and meaning that helped populations maintain psychological resilience despite individual mortality and group losses during environmental challenges. Archaeological evidence suggests that emotional regulation capabilities evolved as integrated systems combining individual psychological skills with social support mechanisms and cultural practices for meaning-making. Psychological resilience was both individual and collective. The development of enhanced emotional regulation also enabled more effective group cooperation and decision-making under stress. Populations that could maintain psychological stability were better able to coordinate complex activities and maintain social cohesion during challenges. Archaeological sites show evidence for increasingly sophisticated social institutions and cultural practices designed to maintain psychological well-being and social stability during environmental stress. Mental health became a recognized component of adaptive capacity. The relationship between emotional regulation development and social organization created positive feedback loops where better psychological management enabled more effective social cooperation, which provided better support for individual psychological well-being, which enhanced collective resilience. Understanding these feedback loops between psychological resilience and social organization provides insight into why human societies develop such elaborate cultural institutions for managing stress and maintaining well-being. Psychological infrastructure was as important as technological infrastructure. The archaeological record also reveals that different human populations developed distinct approaches to emotional regulation and stress management that reflected their specific environmental and cultural contexts. Regional variations in ritual practices and social organization indicate diverse psychological traditions. This diversity in emotional regulation approaches provided human populations with a broader range of psychological tools that could be applied to different types of stress and uncertainty. Psychological diversity enhanced collective mental health and resilience. Archaeological evidence shows that populations with access to diverse emotional regulation traditions through cultural exchange were more resilient to environmental challenges than those with more limited psychological repertoires. Psychological diversity was crucial for maintaining adaptive capacity under stress. The development of mechanisms for preserving and transmitting emotional regulation knowledge became essential for maintaining human psychological resilience. Archaeological sites show evidence for increasingly sophisticated systems for psychological education and support. These psychological transmission systems required not just individual emotional regulation capabilities, but also social institutions and cultural practices designed to preserve and enhance psychological knowledge across generations. educational and support traditions became crucial for maintaining mental health. Archaeological evidence suggests that populations with more robust psychological transmission systems were more successful at maintaining morale and social cohesion during environmental challenges. Psychological infrastructure was essential for long-term adaptive success. Understanding the relationship between psychological transmission and adaptive resilience provides insight into the conditions necessary for maintaining human mental health under environmental stress. Emotional regulation capabilities alone are insufficient without the social and cultural systems necessary to support and enhance them. The study of ancient psychological evolution thus offers important lessons for contemporary challenges related to mental health, stress management, and psychological resilience. The same principles that enabled ancient psychological advancement remain relevant for addressing modern stress and uncertainty. The relationship between psychological evolution and environmental adaptation also reveals how emotional regulation capabilities could have effects far beyond their original adaptive context. Psychological abilities that evolved for environmental challenges became the foundation for artistic, spiritual, and therapeutic achievements. Archaeological evidence shows that periods of most rapid psychological innovation consistently coincided with periods of greatest environmental stress, indicating that emotional regulation development was driven by adaptive pressures rather than emerging during periods of stability. This relationship between environmental stress and psychological innovation suggests that similar pressures may continue to drive emotional regulation and mental health development today. Contemporary environmental challenges may be creating selective pressures for new forms of psychological capability. Understanding how environmental challenges drive psychological evolution provides insight into the potential for continued human emotional and mental advancement. The same processes that enhanced human psychological capabilities in response to ancient climate challenges may continue to operate in response to contemporary environmental changes. Moving deeper into this extraordinary narrative, the relationship between climate and human evolution reveals even more sophisticated adaptations when we examine how environmental challenges affected human time perception and temporal cognition capabilities. Archaeological evidence shows that Middle Stone Age humans developed unprecedented abilities to perceive, measure, and plan across multiple timescales. Archaeological sites from this period show evidence for systematic tracking of seasonal cycles, astronomical patterns, and long-term environmental trends that required temporal cognition capabilities far exceeding those of other species. The complexity of temporal information management evident in these sites indicates revolutionary changes in time perception. The development of enhanced temporal cognition appears to be directly related to the environmental challenges created by climate variability. When environmental conditions became unpredictable on multiple timescales, survival often depended on accurate understanding of temporal patterns and precise timing of activities. Archaeological analysis reveals that human populations developed sophisticated systems for measuring and tracking time that involved astronomical observation, seasonal monitoring, and long-term pattern recognition. These temporal technologies required advanced cognitive capabilities. The emergence of astronomical observation systems during this period required temporal cognition capabilities for tracking cyclical patterns across multiple timescales and integrating information from different temporal domains. Time perception became multidimensional and hierarchical. Archaeological evidence suggests that temporal cognition capabilities evolved as integrated systems combining short-term timing, seasonal tracking, and long-term pattern recognition. Time perception involved multiple cognitive processes rather than single mechanisms. The development of enhanced temporal cognition also enabled new forms of planning and coordination that could extend across multiple timescales simultaneously. Human societies could coordinate immediate activities while planning for seasonal changes and long-term trends. Archaeological sites show evidence for increasingly sophisticated planning systems that integrated information across multiple temporal scales to optimize resource use, social coordination, and technological development. Planning became temporally sophisticated and multidimensional. The relationship between temporal cognition development and planning capabilities created positive feedback loops where better time perception enabled more effective planning, which required more sophisticated temporal cognition, which enhanced planning capabilities further. Understanding these feedback loops between temporal cognition and planning provides insight into why human societies develop such sophisticated capabilities for long-term thinking and coordination. Temporal cognition was a foundation for complex planning and social organization. The archaeological record also reveals that different human populations developed distinct approaches to temporal cognition and time measurement that reflected their specific environmental and cultural contexts. Regional variations in astronomical observation and seasonal tracking indicate diverse temporal traditions. This diversity in temporal cognition approaches provided human populations with a broader range of time perception tools that could be applied to different types of temporal challenges. Temporal diversity enhanced collective planning and coordination capabilities. Archaeological evidence shows that populations with access to diverse temporal cognition traditions through cultural exchange were more successful at long-term planning and coordination than those with more limited temporal repertoires. Temporal diversity was crucial for adaptive planning. The development of mechanisms for preserving and transmitting temporal knowledge became essential for maintaining human planning capabilities. Archaeological sites show evidence for increasingly sophisticated systems for temporal education and knowledge preservation. These temporal transmission systems required not just individual time perception capabilities, but also social institutions and cultural practices designed to preserve and enhance temporal knowledge across generations. Educational traditions became crucial for maintaining temporal cognition. Archaeological evidence suggests that populations with more robust temporal transmission systems were more successful at long-term planning and adaptive coordination during environmental challenges. Temporal infrastructure was essential for sustained adaptive success. Understanding the relationship between temporal transmission and adaptive planning provides insight into the conditions necessary for maintaining human long-term thinking under environmental uncertainty. Temporal cognition capabilities alone are insufficient without the social and cultural systems necessary to preserve and enhance them. The study of ancient temporal cognition evolution thus offers important lessons for contemporary challenges related to long-term planning, temporal coordination, and future thinking. The same principles that enabled ancient temporal advancement remain relevant for addressing modern temporal challenges. The relationship between temporal cognition evolution and environmental adaptation also reveals how time perception capabilities could have effects far beyond their original adaptive context. Temporal abilities that evolved for environmental challenges became the foundation for scientific, technological, and philosophical achievements. Archaeological evidence shows that periods of most rapid temporal cognition innovation consistently coincided with periods of greatest environmental uncertainty, indicating that time perception development was driven by adaptive pressures rather than emerging during stable periods. This relationship between environmental uncertainty and temporal cognition innovation suggests that similar pressures may continue to drive time perception and temporal thinking development today. Contemporary environmental challenges may be creating selective pressures for new forms of temporal capability. Understanding how environmental challenges drive temporal cognition evolution provides insight into the potential for continued human temporal advancement. The same processes that enhanced human time perception capabilities in response to ancient climate challenges may continue to operate in response to contemporary environmental changes. The narrative takes another remarkable turn when we examine how climate-driven evolution affected human pattern recognition and analytical thinking capabilities. Archaeological evidence reveals that environmental challenges drove the development of pattern recognition abilities that provided the cognitive foundation for scientific thinking and systematic analysis. Archaeological sites from the Middle Stone Age show evidence for increasingly sophisticated approaches to pattern recognition that involved identifying complex relationships between environmental variables, technological parameters, and social dynamics. These analytical capabilities went far beyond simple association learning. And so here we are, millions of years later, carrying within ourselves the living legacy of every climate crisis our ancestors faced and conquered. Every time you adapt to a new situation, every time you innovate under pressure, every time you cooperate to solve an impossible problem, you're channeling the same climate-forged capabilities that transformed a small population of early hominins into the most adaptable species Earth has ever known. The changing climate didn't just shape our bodies and brains, it sculpted our very souls, creating beings capable of thriving anywhere from Arctic tundra to tropical rainforest. Understanding this deep history reminds us that we've always been a species defined not by our environment, but by our ability to master any environment through intelligence, cooperation, and relentless innovation. Thanks for joining me on this incredible journey through deep time, and remember, the next time you face a challenge that seems impossible, you're equipped with 4 million years of climate-tested human ingenuity.